2. Apologies for being a little bit late. I found some more data I wanted to add. Couldn't help myself. I had responded poorly to a question from Jeff yesterday. He was asking about a quote from the Shanahan paper where Shanahan was arguing that the signal to noise ratio was very good. And in fact, I went and checked the paper, and that's what he said. His argument is that excess heat is due to a systematic error in the calibration constant. So if you have an excess heat burst, during the time the excess heat burst, the calibration constants change. That's the argument. A little bit on the silly side. So it is. Anyway, once again, the warning. Summary of day 1, we did a lot of stuff on day 1. The big issue here is that we affect excess heat, no commensurate energetic nuclear radiation. Positive results. The big issue is that if it's real, it presents it's inconsistent with nuclear and condensed matter solid state physics, and that's the big issue. The large number of negatives that were reported, as we saw yesterday, the significance of those have been overstated. We saw for 217 negative experimental papers that only a fraction of them actually did any calorimetry. Only a fraction of those worried about the loading, and none of them reached a loading that we would consider to be what you would need to be sure that you would see excess heat. So we're going to begin today by trying to understand a little bit better what makes it hard to get a high loading. And the argument ultimately is going to be relatively straightforward. But in order to understand it, we're going to need to do some basics. So last time we began thinking about the phase diagram. So here's the phase diagram. So the idea is you put a piece of palladium in contact with gas and you increase the pressure. So here's the pressure in atmospheres, 1 atmosphere, 10 atmospheres, 100 atmospheres. Here's the loading. So a loading of 1 is out here. You can see because these lines are going up, you need very high pressure to get the loading. You have different lines because of course we're at different temperatures. So these are called isotherms, so constant temperature lines for concentrations of functional loading. You might say, well, what does this have to do with electrochemistry and what we're trying to do? Well, basic arguments, you can learn a lot from this. Here's an equivalent one for hydrogen, deuterium, tritium. You find that deuterium, you need a little bit higher pressure than hydrogen. And this difference actually allows you to use palladium to separate hydrogen from deuterium and tritium from deuterium and hydrogen. Question is what's going on in the miscibility gap? This is called the miscibility gap. And the pressure is roughly constant while you're loading going through the miscibility gap. So I've been curious for a while. What's going on in the miscibility gap? I found a cool paper in the literature. So in this experiment, this is a function of time. This is basically loading, 20%, 40%, 60%. And this is a function of time the cathode was loaded. And during the time the cathode was loaded, X-ray spectra were taken. So this is the X-ray spectrum for unloaded palladium. And 20 some odd percent loading, 40 some odd percent loading, 60, almost 80% loading. And so the question is, how does the spectrum go from low loading to high loading? So for example, yesterday we showed a plot showing that lattice constant change continuously as a function of loading. Of course, that was done under different conditions than this is done. What we see is basically that the spectrum that you get for unloaded palladium is getting phased out, whereas the spectrum associated with the loaded palladium is being phased in. And that's really interesting, because that tells you that in in the miscibility gap, what you've got is you've got some of the phase here and some of the phase over here showing up intermixing. So you don't have a continuous in concentration. You have islands of the two phases in the miscibility gap. So you can see that here's the lattice constant for the alpha phase, here's the lattice constant for the beta phase. And as the data was scanned going from low loading to high loading, what happened is you have the alpha phase persist for a while, but the signal gets weaker, and the beta phase kicks in, and its signal gets stronger. And then the lattice constant increases as you get to higher loading on the other side of the miscibility gap. It makes it pretty clear what's going on. Something similar happens in nickel, as we'll talk about later, except that the significance will be far more interesting. We'll know more of that when we talk about it. So anyway, we're interested in the phase diagram. The phase diagram is complicated because it's got a mixed phase region. Increasing the pressure at higher concentration means harder to achieve high H to PD loading or equivalent D to PD loading. Let me pause for a moment. Comments or thoughts or questions? Okay. So I'm interested in the chemical potential next. How do you think about a chemical potential? Well, if you think about the chemical potential for electrons, you're thinking about the Fermi level, and basically you're thinking about the voltage. So the chemical potential for hydrogen is basically the equivalent of the voltage for electrons, negative voltage. So more hydrogen loads and the pressures increase. In order to understand this theoretically and figure out what the chemical potential is, we need to have a way to measure it and determine it. So you can measure the pressure and the loading. You can weigh your sample as you increase the pressure. Early in the 20th century, the statistical mechanics of hydrogen as an ideal gas became understood. And that's really important because we have equilibrium between the gas and the hydrogen in the palladium. Now we have a reference against which to test the chemical potential, because the chemical potential in the gas, once the models were worked out, it is known very well. So let me show you briefly. The issue is that the expression was obtained for the entropy. And having an analytic exact expression for the entropy for this model is like being handed the keys to the kingdom. Once you have it, you can calculate the temperature, the pressure, the chemical potential in terms of derivatives of the entropy. And for example, this one gives you the ideal gas law. This one gives you the average thermal energy per particle. And this one gives you an exact expression for the chemical potential for the model. So inasmuch as hydrogen gas is an ideal gas, you know that chemical potential is, in this case, associated with the kinetic degrees of freedom. So what that means is that you can make the following assignment, that if you put palladium in and let it come to equilibrium with gases and pressure, then if you want to know the chemical potential of the hydrogen and the palladium, well, in equilibrium, it's going to be the same as the chemical potential of the hydrogen and the gas, which is actually going to be half the chemical potential of the hydrogen in H2 as a gas, because it's molecular hydrogen. So these guys, we can figure out, physicists were able to figure it out once the ideal gas law was understood for hydrogen. Now, there's a minor headache. Hydrogen is actually not an ideal gas. This model works in this range right here. So it works down here to pressures of maybe hundredths or few hundredths gigapascal. So the question is, what the heck is a gigapascal? Well, 2 or 3 gigapascal is like 20 or 30,000 atmospheres. So atmospheres down here. So you can actually go to relatively high pressure ideal gas law, but if you want to go to pressures needed to get high loading, you actually have to go all the way up to gigapascal or more. So the question is if the hydrogen is not an ideal gas, what do you do correct? Actually, first question, since I was working on this problem, I was curious as to, and the issue is that hydrogen comes close to hydrogen, they push each other. Here's potential models. This one was the one calculated sort of exactly for ground state molecular hydrogen. This one was an earlier one. It turns out that if you use this one, you get to a higher pressure. If you use one a little bit lower, you get better beam experiment. There's higher order angular momentum terms that are involved. So here's a calculation I did, this red line of solving Newton's laws of this potential, molecular dynamics. And I get a halfway decent fit. This Ross potential is a little bit on the soft side. The other one's a little bit on the hard side, though. The other one on the other side ends up being on this side of the curve. But, so in order to correct the ideal gas law, if we start out with the ideal gas law, we can write it in this form. It's logarithmically dependent on the pressure. The only problem is that if your gas is not an ideal gas, then this is going to give you the raw chemical potential. So a very famous electrochemist, Lewis, back years ago, proposed to retain the form of the ideal gas law, but it was found that you could replace the pressure by the fugacity. And once you did that, you could then use, if you replace pressure with fugacity, you could use for the ideal gas law, the corrected version of the fugacity. And if you have the equation of state, you can figure out the fugacity by doing the cynical. So there's models out there for this. Bacchus was a big fan of the model by Pauli et al. It was built at Los Alamos back in 1959. It's in blue on this curve, at least on the set of curves done at room temperature. There's a more recent one. This one's fitted to lower energy data. The fact that the curve's over means I'm looking at the curve out of the range of the fit. The one in red is one that in recent years has actually been the standard. And when my student was doing a PhD thesis, he plotted the standard against Bacchus's favorite, and they were different. I've been thinking, why the heck are they different? And it turns out they're different because the boundary condition or pressure for this one doesn't go to an ideal gas law. So when you calculate the fugacity of it, you get an offset. It turns out that people who have been using this one recently to calculate the fugacity and getting answers a little bit off. Turns out I found in the literature recently by Frenchman Gilbert that looks very good. And this is the best one out there these days. Now you're going to say, well, the differences don't matter so much, so it's not a big deal. I was interested in the question of what's the difference between hydrogen and deuterium, given that in years past, people said, well, for fugacity for deuterium is the same as the fugacity for hydrogen. But the pressure is a little bit different. You can see hydrogen and deuterium is a tiny bit, and the points are displaced, but the curves are offset by a little tiny amount. Joubert did a fit for deuterium and one for hydrogen. And in this fit, there's a 4.5% difference at about 1.5 gigapascal. And if you compare that against experiment, you don't see that. So I'm scratching my head and thinking, well, the deuterium data is there's less of it, the fit's not quite as good. And so I think believing in this is a little bit, I think it's not reliable. I think if you use Joubert's fugacity to tell the difference between palladium or deuterium and hydrogen, you're going to overstate the difference. Anyway, so now that we have the fugacity, well, we have the equation of state, we have hydrogen, we have non-ideal, we have fugacity, and things are in pretty good shape, so we can use that to begin to interpret the phase diagram in terms of chemical potential. And once we do that, we're going to understand why it's hard to load palladium. So here's a model that was done by my student for a PhD thesis. He took points, basically took points from this kind of curve and extended them out as far as it went. And then in the literature, there's occasional measurements and extrapolations to higher loading. So, for example, in order to get to a loading of 1, for palladium hydride, you need a pressure of 10,000 atmospheres of hydrogen gas at each equilibrium. We recognize that as being a very high pressure. In the case of deuterium, this is sort of a similar exercise, taking data from various sources and then extrapolating it to higher, where, again, experimental data is available. Baranovsky took some data points actually beyond the loading of 1. So we actually know the points down here, know the points up here. And it's a matter of trying to fit a curve in between. Now, with the pressure as a function of loading, given that we can reference against the chemical potential of deuterium gas, we can develop this as a chemical potential model. So I've referenced that this is relative chemical potential. I've referenced it to 0 in the miscibility gap, and then it goes up, and then around the loading of 1, it gets a kick, it goes even higher. And I contend that this curve is, it tells you, when you have physics background, this curve, the shape of it, the fact that it goes way up, is more than enough to explain to you that it's very hard to load palladium at very high loading. Basically, the chemical potential going up like this basically means that you have to push really hard to get the deuterium to go in. The deuterium doesn't want to go in. If you think about it, KT is a 40th of a volt. It's a sort of a tiny number here. But you're talking about, to go from a miscibility gap to 0.8, you're talking about going up like 120 millivolts. And in a sense, that's why we saw yesterday that the folks who tried replications of Fleischmann bonds, they reported loadings generally at 0.8 or lower, which it is accessible if your electrochemistry is not particularly great. On the other hand, we saw that according to the SRI data, we had to get a loading of 0.95 somewhere during the loading history in order to see a positive result at SRI. So the difference goes from here up to about here. You've got something in the neighborhood of 200 millivolts more chemical potential. That's gigantic. That's heroic. That means that in order to get a loading of near 1 by electrochemical techniques, you have to really know what you're doing, and you have to do a good job. And shortly, we're going to understand what that means in more detail. Let me pause briefly to come in response to questions on this. You want to breathe?
Yeah. So this kind of signature, outside of, say, cold fusion, are there other realms where people see this and are?
What you mean, where the chemical potential is useful?
Yes, and where it has this particular characteristic.
As it turns out, the chemical potential is really important for the physical chemists because they can only understand reaction kinetics. That's what we'll show shortly from a knowledge of the chemical potential. I was reading through the literature to see if I could find a curve that I could plot against this one. And found one plotted in Physical Review, PhysRed D, and I was going to pull it out and plot it and show it to you, but it was a theory calculation done with a method that's not very accurate and was way the heck off. So I didn't bother, but I did make a curve a while back, basically showing my fit of the chemical potential against the data, well, something called the Fromkin absorption isotherm, which is basically the slope of the curve above the miscibility gap. So Chen and Rod did some AC impedance studies, electrochemical studies of loading palladium, and from the phase they were able to deduce the slope of this curve. And the blue curve then is the basically using their result for the slope and hooking it together with the model that includes entropy terms. The blue curve is what Chen and Rod would have gotten, whereas the black curve is what I got from the. They're a little bit off, but given that these are from opposite kinds of, very different kinds of experiments, it was actually stunning to me that they were so close. And in fact, one could probably go back and either correct one set of data or the other set of data to get a better number by making use of both of them together.
It's so interesting to try to integrate chemical potential as an electrical engineer. I'm having a little trouble. Since ICCF 10, we pointed out that we get excess heat with a legacy VOC of 0.7, and we're really happy when we get the open circuit voltage of 2.4 because we're getting a lot of excess heat out. How do we connect up that? Are we dealing with the chemical potential of the cathode minus the anode? Because it's the different. There's a term missing.
Let me see if I can find a slide to make that clear. Okay, Storms did some experiments a while back where he measured the open circuit voltage under conditions of different loading. So here's the D to PD ratio. And the one I want to draw your attention to is these curves. This one was done sort of fast. These were done slow. And when you're done slow, you end up seeing that when you get above the miscibility gap, the open circuit voltage begins to increase. And it turns out that the increase, the slope of the increase, and there's different factors that contribute to the open circuit voltage, one of which is the chemical potential of deuterium. In this case, the slope that you get here is basically consistent with this slope. You're going from 0.6 to 0.8, it's 160 millivolts or thereabouts. You're going from 0.6 to 0.8, and this is maybe a little bit more than 160 millivolts. So it's a contributing factor, but it's not the whole story.
Well, that means we can also determine the composition from VOC.
You can get information. You can get relative information about the loading from the VOC. That's true, and that was done in some really negative experimental results as well. Takeaway message: you can load, easy to load to 0.6, hard to load higher than 0.6. You can understand, we actually now have a way to characterize it with the chemical potential, and you can understand the chemical potential in terms of physics type terms. And we've even now, at this point, got some measure of confirmation of chemical potential that we derive from the load-in experimentation is consistent with what's measured from the ACP state. Other thoughts or comments or questions? Okay. I'm next interested in deuterium diffusion. So, let's see, diffusion. How boring can we get? But it turns out it's actually interesting and it's relevant to the idea. So, you start out, you go to the textbooks, and the textbooks say, textbook in this case is Fukai's book on metal hydrogen system. You get a constant out in front, you get an even minus delta E or KT factor. Delta E is 206 millivolts. You've got an occlusion factor, so if you're places where you're trying to go to are already loaded, you can't go there. And there you have it. What's interesting is that the diffusion of hydrogen or deuterium and palladium is fast. So here's what fast means. Here's how far you can diffuse as measured by square root of L d tau. Here's tau. So for example, here's 1,000 seconds, roughly 20 minutes. In 20 minutes, you can go 200 microns. If you're going to wait a few hours, you can get just about 2 millimeter. And so what that means, back in 1989, cathodes that Martin Fleischmann was working with were millimeter-ish kinds of cathodes. So you should be able to load very quickly. They loaded for a month. So, and that was found to be a requirement that you had to load for a very long time before you could see excess heat from the initial Fleischmann experiment. So already this is sort of an interesting number because it's telling us that there's more to the story than just getting the deuterium in the cathode. So if I take Fukai's textbook number and go down here, I get a line sort of like this. Baranowski did some measurements of very high loading. If I plot his data points as a diffusivity on this curve, it looks like this. And scratching my head thinking, curve, what's the difference? Turns out it's going to be worse than that. I can take the Baranowski data and I can fit it. I can get a continuous curve, so that gives me a model for diffusion for the high loading region. But if I look at the experiments of Mengele and Fabrizio, so they did an experiment where they flowed hydrogen through palladium and measured the diffusion constant as a result of these experiments. So the Fukai's textbook number is up here, and over here we get numbers that are sort of consistent with that, but this is the high loading regime, and we remember that Baranowski's numbers are a little bit higher. So there's higher numbers here, which are sort of going consistent with Baranowski's measurements. But here in the miscibility gap, we're getting really small numbers. It's down by a couple of orders of magnitude. So scratching my head saying, well, I want my money back. My textbook should have told me about this. But as it turns out, it's relatively easy to resolve. The idea basically is due to Onsager. And the very simple way of thinking is that if you have a chemical potential, can we think of a chemical potential like other potentials? For example, if I have a gravitational potential and I drop something, there's a force and it falls. If I have electrostatic potential, I have acceleration. So I have a chemical potential gradient. When chemical potential is high where the loading is high and it's low where the loading is low, can I think of the chemical potential gradient as giving rise to a force that's going to drive diffusion? That's the basic idea. And of course, it was a good idea. And what that means is that if gradient mechanical potential is driving diffusion, if you're in the miscibility gap and you've got a flat chemical potential, you're not going to have very much diffusion going on. So this is the reason why the diffusivity is so low in the miscibility gap. So what you could think of doing is you could maybe hook up some kind of model where you use Onsager diffusion in the regions where you've got a difference in the chemical potential. The miscibility gap maybe revert back to some simple diffusion kind of model. Now, if you do this, you still need a number for the diffusivity and the miscibility gap. It turns out there's some experimental data where it's been measured by NMR. So for simplicity, I put a flat line here at the number that corresponded to the NMR measurement. And then here I've got Baranowski's data. And here's the range over which Fukai is. So we now have a model for the diffusivity of deuterium near temperature. That's what it looks like. It looks a little bit funny. But, so that's the story. We've got a model. And now I'm kind of beginning to scratch my head and wonder what happens because we've got a very low diffusivity and miscibility gap. Let me pause for a moment. Are there comments or thoughts or questions? Any takers? Yeah.
Question. You heard my misunderstanding of it, but it seems funny that it's the gradient of the chemical potential that would drive the diffusion. Why is it gradient as opposed to just the inherent nature? So you're saying it's sort of a system problem as opposed to an atomic problem?
No, I mean, in a potential, if you're going skiing at your top of the hill, if you're at the top of the hill and it's flat and you're standing there, you're not going to accelerate. On the other hand, you take a step on the slope, now you've got a gradient, you're going to go zooming down and you're going to go zooming faster and faster. So it's the gradient of the potential that gives rise to the force. The only issue with respect to chemical potential is whether you can think of the chemical potential as sort of like a potential. And if it is sort of like a potential, that would imply that you get sort of like an effective force. Like you could think of it as an effective force due to the gradient of the chemical potential. And this kind of diffusion model argument and the reasonably obvious agreement with experimental data suggests that point of view actually works. That's right. Okay, so I'm going to think a little bit about the diffusion profile. So if you have zero diffusivity and you have a constant flux, what that means is you're going to have a very sharp slope. Or for example, if you have finite diffusion coefficient, then a modest slope in the concentration profile gets you a flux that goes here. A modest slope gets you a flux that goes in here. But if you've got a break in the, if you've got a small diffusivity, you have to have a very large slope in order to get the same amount of flux. So this was done for a simulation. I wrote out code and did a modeling for the loading of a cathode. And this is the kind of answer I got. So I got this big step. That's strange. I bet that's a bad thing. It's going to be a bad thing, especially because we saw that there's a 15% volume change going from a loading of 0 to 1. So you have a giant, a very large relative lattice constant, small lattice constant. So you have a big jump in the stretching of the lattice. So there's a big stress gradient. And the thought is that can't be good. Now the question is, are we sure that it happens in real life? So it turns out there's this guy, Skorodumov, who has this setup to do neutron scattering from interstitials in metals. And using 14 MeV neutrons in small angle scattering, he was able to resolve the profile of the of this front of this discontinuity going through. So the basic picture is you come out and get a discontinuity. You go from minimum concentration to maximum concentration to minimum concentration, and you do it in a step. Well, this is alpha max, alpha phase, beta minimum phase. That's the concentrations associated with phase boundaries. Anyway, you end up getting a reasonably sharp step here. Looks like there's a little bit of spreading, so the material is not perfectly uniform. There may be some spread in the diagnostic itself. But the basic issues, you could see it from this neutron scattering data. It turns out you can also see it from morphological studies. I didn't have a good plot to show you, but it's in the literature. It turns out there's yet another effect. If you've got this big volume change, you're straining the lattice that induces a stress. The stress adds to the chemical potential. So now you need to solve this not only just with concentration and chemical potential, but the stress-induced correction of the chemical potential. This has been studied by many groups. There's groups that do experiments that look at it. There's groups that have done theory looking at it. This is a group from Los Sapiens, and our friend Vittoria's co-authored this paper. And basically what they find is that when you add the stress effect, I was hoping it's going to smooth out the discontinuity, but it doesn't have much impact on the discontinuity, but it impacts what happens in the beta phase a lot more. That's the conclusion of what's going on with stress. Okay, so loading is going to degrade the palladium. The idea is that you get this big discontinuity in concentration. You have this expanded material on one side of the discontinuity, this unexpanded material on the other side. As it plows through, it basically grinds up the palladium. The solubility is lower, dislocation vacancies are reduced. And that's why electrochemists historically have loaded very, very slowly when they're going up past the miscibility gap. Alternatively, preload at elevated temperature where there's no miscibility gap. Let me show some curves. So here's an experiment done. This is solubility. Piece of palladium. But if you're taking the palladium and you've loaded it, gone through the alpha phase boundary, you come back, solubility is lower, and you can see it. You also get a hysteresis in the loading curve, so you need more pressure to get the same amount of loading after you've loaded and come back. You can also see it in dislocations. This data I thought was extremely interesting. So in Japan, they're doing these positron annihilation. So they have their sample, they're loading it, they put in positrons. Positrons annihilate with electrons. So they go through the lattice, they find the place where the fewest electrons are, and they sit there, and they wait until they annihilate with another electron. And the time that it takes depends on how many electrons are and where they're sitting. So the positrons go, they look for the minimum electron density. And so the longer the lifetime, the lower the electron density. So this group's published a number of studies which are like, extremely interesting to show this kind of effect. But this one, I thought you get to see a story about loading above the miscibility gap. So this black data here, it's loaded at 623 Kelvin, which is above the miscibility gap. So there's no miscibility gap, there's no damage to the lattice. So the lifetime, this is annealing temperature. So what they're doing is they're increasing the temperature. They're starting with a loaded piece of palladium that's loaded at high temperature, and then they're raising the temperature to drive off the deuterium, the hydrogen in this case. So they get a lifetime that's like 124 picoseconds, which is longer than in pure palladium, which is 106 picoseconds. So they say, oh, what's going on here? Well, what's going on is the lattice is stretched out a bit. So the electron density is a bit lower where there's vacancies than for the pure lattice. And then lattice constant changes from 3.88 up to 4.07 or thereabouts. So as the hydrogen is driven off, as you can see happening here, you go down to the crystal number, which means basically this is a signature that there's no vacancies going on, participating. Here, they've done the same kind of thing. They've done it near room temperature. So once they've loaded, it had this big discontinuity go through. It's ripping up the lattice, it's making defects, it's making vacancies, making dislocations. It turns out the positrons find them. So you put the positrons in, they look around and say, where's the electron density the lowest? What's the lowest of the vacancies and the dislocations and so forth? And so you can tell from the positron emission studies both that they're there, you can tell what kind they are, and you can even tell how many there are. And then when you anneal out the dislocations and vacancies and come back down and it goes back down to the crystal. I thought this is really cool data to share. You also have the issue of grains. It turns out that between the grains, you've got passages where you have very high hydrogen and deuterium diffusivity. So having grain boundaries is sort of a very bad thing. Also, if this discontinuity goes through, it takes big grains and chops them up into smaller grains and makes much more boundaries, which hurts in terms of getting loading. Deuterium diffusion palladium is fast. But the miscibility gap gives us a region with very low diffusion coefficient, which makes discontinuities and loading, which rips up your lattice and makes it very hard to deal with, reduces solubility, and so forth. Let me pause for questions and comments and thoughts. Any takers?
Are there ways then not to use the metal in a crystal form, like palladium aerogels or something that works on a smaller surface, so you don't have the crystal effect?
Mitchell will talk some about that probably tomorrow and Friday in his experiments. But yeah, there is. But in a sense, even though we see this and it's bad, the way to get around it, the obvious ways to get around it is just to load ridiculously slowly and minimize the gradients, or load at high temperature initially, get above the miscibility gap, and then you're good.
Any experiments have been done with single crystal
Yeah.
to avoid boundary issues?
Actually, people did single crystal experiments back years and years ago. And they loaded it and they did X-rays studies. And what they saw is that when they loaded reasonably rapidly, that the single crystal turned into a gazillion polycrystalline regions. There's literature that shows, for example, this positron study basically is showing you that if you go above the miscibility gap, you're good. And there's many other studies in the literature as well. We talked a little bit about resistance ratio. Mitchell mentioned it last time. So if loading is so important, we'd like to figure out how to keep track of the loading. So there's lots of ways. X-ray neutron studies, you can measure lattice parameter. Chemists have good ways to measure the catalytic volume. You can weigh it. You can look for worth in oxygen. It turns out the popular method is to look at the electrical resistance. If you look at the resistance, in the early years, this calibration curve was used. think, why does it go up and why does it go down? Well, if you look at the old literature on metals, you find out that in the case of alloys, people notice that the resistance would go up and would come back down. Basically go from 1 roughly to 2 back to 1 for different alloys. And it's an effect of disorder. So if you have pure palladium, crystal palladium, you've got a nice ordered crystal. If you have palladium deuteride, palladium nitride, you have a nice ordered crystal. But if it's partially loaded, then half the octahedral sites are vacant and half are occupied, which means particle going through is not going to be seeing, it's going to be seeing a random disordered lattice, and that makes the conductivity, the resistance go up. And it comes back down because you're increasing the load. So a better calibration curve was established for the high end of this. If you look, it goes slow, goes up, goes down. So if you're loading, you're going to go from low resistance to high resistance and come back down again. So here's the going back down again in the high loading ratio. So once a more accurate resistance ratio curve was established, people could basically do better, more accurate measurements and figure out what their loading was during experiments. So takeaway message is we now have a way to figure out what our loading is, and it's a reasonably convenient measurement to do an electrochemical experiment. So once it was propagated, a lot of groups did these measurements. Comments or questions or thoughts?
Well, it's important that they overestimated early on.
Yeah.
It seems like there's a large literature, large body of literature on the use of palladium for as a catalyst. It gets into the resistance ratios and so forth. When we were looking at Chilani's results from a couple of years ago, turned out we found that there was a lot more to the story than just the resistance ratio as it was being used, at least by Chilani. Have you looked at that big body of literature and catalysis?
The big body of literature is not as big as all of that.
Okay.
One thing that's well known is that in some of the early cold fusion experiments, they determined their loading by weight, and some studies had been done earlier comparing resistance ratio measurements by weight measurements. And it turns out they give different answers, and the idea is that a resistance ratio measurement gets the internal loading sorted out. On the other hand, if you're doing weight, you pick up the loading due to hydrogen in traps and hydrogen hanging out on surfaces, and so forth. So you tend to get a higher loading estimate based on a weight measure that you do by resistance ratio measure. So there is definitely more to the story. It's more interesting. The resistance ratio measurement, at least in this field, is preferred these days because it's getting at the internal loading, which is more important.
Yeah, I think where we read into this was in the copper nickel, actually, rather than palladium, which is what he was using.
Right.
Copper, the constantan mixture is widely used, I guess, as a catalyst.
Okay, so we're interested in why the cathodes are hard to load, which draws our attention to basic electrochemistry models. And again, these kind of electrochemistry models are enough to put interesting punchline here, which you'll see. We can actually learn something about what was going on in the early experiments by spending a little bit of time thinking about this. The mechanisms for loading, at least on a clean, pure metal surface, are studied in the literature. They're called hydrogen evolution reaction, deuterium evolution reaction. And recently looking back in the literature, found that the first person to use this nomenclature in the literature appears to be John Bockris, back around 1950. He's a big advocate of these models. Apply to many metals. If you think about electrochemistry as a theoretical problem, it is ridiculously difficult. And in a sense, it's kind of amazing to me that anything works. And so I view these hydrogen evolution reaction things as basically one of the big success stories for electrochemistry. They're described in textbooks. The folks involved in reactions have Nobel Prizes attached to them. And it's interesting. Let me think a little bit about it. To get deuterium to go into palladium, come in with a D2O molecule. At the surface, an electron is given, a deuterium atom is given up to the metal, an electron is given to the OD, and that's basically the Vollmer mechanism in base. There's a different Vollmer mechanism in acid. The cool thing about this is that you get one deuterium atom deposited basically on the surface for every electron given up to the species that's leaving. And in a sense, that's really cool because if you can measure the current, the total charge delivered, you can figure out the total number of deuterons delivered to the surface. And at low concentration, those deuterium atoms go into the metal, which means if exactly the number go in the course of the charge, then you're at 100% ferrotenic efficiency. And these experiments at low loading, low concentration electrochemistry seems to run very, very near 100% ferrotenic efficiency. High loading, you don't. So another intuitive way of thinking about it is you can turn the current on, and you know when the current's going on, you're depositing deuterium on the surface here. If you want to deposit more, you turn the current up. If you want to deposit left, you turn it down. And if you want to take them off, you turn the current the other way. To get rid of the deuterium, surface deuterium leaves as gas, just basically by coming close to one another and then finding the potential minimum to tunnel through and they leave. This is well studied. It's called the Tafel mechanism. Not connected to current or anything. There's another reaction mechanism which has been discussed in connection with palladium deuterium. It's called the Hyrovsky mechanism. And if you think of Vollmer as like Santa Claus comes, brings gifts, leaves them under the tree. We can think of Hyrovsky as the Grinch. So the Grinch comes and takes the presents and takes them off. So it works a little bit like Vollmer. You pick up a charge. The only thing is you're deloading with Hyrovsky. Hyrovsky requires deuterium on the surface, so Hyrovsky, if it occurs, would occur at high concentration, but not at low concentration. You can model these things. This may look like an ugly, complicated equation, but it turns out there's some simple stuff associated with it. If you're going to load, you need for some sites to be unoccupied. So 1 minus the loading, this tells you sites unoccupied. Turns out that if your chemical potential of your hydrogen is high, then you don't leave hydrogen and deuterium so often. That shows up as this factor. And it turns out that if the chemical potential of the electrons is either high or low, if it's high, then it's easy for the electrons to come off. If it's low, then the electrons don't want to come off. That's this factor. And so, in a sense, so this is the detailed balance version of the inverse process. But in a sense, the modeling of it sort of does kind of like exactly what you'd expect it to do and no more. And you have some fitting parameters here in order to, the first principles calculation of the Vollmer, the rate of the current as a function of everything is a non-trivial thing to do. It's been done in the literature, but at this level of modeling, you basically just fit it to data. So for the chemical potential, there's a linear constant, namely the chemical potential is to assume to be linear in the loading above the threshold. So here's the threshold, here's linear in loading, and this slope was measured by Chen and Ra. Here's the slope that's measured to be 0.514 EV per H for where H is the incremental loading, which gives you a Frumkin adsorption parameter, which is 1 over kT times this number. For the free factor here, you can fit against some data. So you have measurements published by Green and Fritz, by Bacchus, by Akita. So you can fit the numbers. You can also get the coefficient here that has to do with the electron chemical potential. So from these data, you can get both terms, which basically means you can get a quantitative model for the Vollmer part of the reaction, the loading part, which means you can now start modeling the electrochemistry. In the Tafel regime, you get a similar kind of model. And once again, you can think of it as sort of simply, if you want to have the deuterium get together and leave, you have to have deuterium on the surface. So it goes like the square of the surface concentration. Here, you have the chemical potential shown now. So higher the chemical potential is, the faster the gas is going to come out. And then you've got factors that you have to fit to experiment. And you can't fit to experiment. There's no trouble with it. What's interesting is that if you assume that the Tafel is in equilibrium with the Vollmer, you can figure out what the loading is based on how much current you've got and how much loading you've got. So you set the Vollmer current equal to the Tafel current. What's coming in matches what's going out. So one expression, other expression, you do some simplification, you get an expression that looks like this. It's called an absorption isotherm. So you can get the surface concentration of the hydrogen and deuterium basically by solving this. If you have some experimental data, and you can use this experimental data now to figure out the Tafel current. And once you've got the Tafel current, you can get the Tafel current from least squares. And the Tafel current gives you the absorption isotherm gives you this line. The experimental data gets you this line. And this will be overpotential. It tells you something about the electron part of the problem. But what you find is you can actually understand the electrochemical measurements in the low loading regime based on a simple Vollmer-Tafel model. And it's fantastic. It's widely used in the literature, and it's used to understand electrochemical measurements. You can do an awful lot more with this than what I've shown here, but this is just the first step. This is of interest to us in understanding what makes things load and not. There's measurements. Here's Green and Britt's measurement. These are two different lithium deuteroxide measurements. But these are measurements. It's 1996, but this is sort of typical what's in the literature. And this is the reason that when Huggins asked Nate Lewis, he says, well, your loading's not, didn't ask, he said, well, your loading's not high enough, that's why it's not working. Nate Lewis was aware of the literature values for these things, and said, our loading's perfectly fine, we get what everybody else gets. It's just there's no effect. So these numbers can be fit to the Vollmer-Tafel models. And I emailed Brits to ask him, Green and Brits. I asked them, I said, what is the difference between these two curves? Because the lithium's present. But I was trying to make a model for the lithium kinetics as well to add it in to try to fit these. I found it to be very difficult. He said, no, this is just differences in the two cathodes. Okay, now all of this actually brings us to the key. We've argued that it's hard to get high loading, and now we have models, so now we can be more precise about it. So we saw that the MIT experiment got loading about 0.75. The Caltech experiment got loadings up to 0.8. And we were arguing that these loadings are way too low to do any good. Nevertheless, these loadings are consistent with the Vollmer-Tafel model, so we get by fitting the data in the literature. So this is sort of consistent with what you'd expect, which leads us to ask the question, why in the world can we get, why should we believe we could get loading particularly higher with an electrochemical loading? We talked about this last time. So here's the excess power in experiment SRI. Here's the D to PD loading. So if you take the loading points and the power points and plot them together, you get this curve. So the excess heat is higher at high loading. But these loadings, if you look at them, this is 0.85, 0.91, 0.95. So we're we're talking about a regime of loading, which doesn't seem to be on Green and Britz's plot. I mean, Green and Britz's plot ends at 0.82 here, but we're talking about getting loadings way the heck up here in order to see excess heat. So the question is what's going on? And more importantly, what's going on with respect to our models? Namely, our models don't seem to be predicting the possibility of getting such high loading. There's another, Kunimatsu and the company, excess heat as a function of loading, sort of getting a confirmation that we need to have higher loading to see an excess heat effect. So I want to come back to thinking about this high loading. It's got this data, Green and Britz data, and from the Green and Britz data, I can fit my Vollmer and Tafel curves, and my Vollmer and Tafel curves thus fit, telling me that I'm not going to get to higher loading. Because once you've established the Vollmer and Tafel prefactors, you get the curves basically across the whole Vollmer and Tafel range, and you can extend it if you have a model for what's going on at higher current densities. But at higher current densities, basically things tend to come down. So here's a Vollmer Tafel regions here. Once you get to higher current density, it's observed experimentally to go down. And Zhang et al. Tried to model this using the Hairovsky mechanism. Look at the later literature in electrochemical studies. There's actually no evidence on Hairovsky's going on at all. And I think there's another explanation for this, which is retrospectively obvious. So the question you should be asking is, why should I believe that loading, anyone's achieved a loading of about 0.84? So here's some data from measurements of SRI. So this is the resistance ratio that goes up to about 2, which means you're going over the hump. You start out with no loading, you go over the hump and you come down. And when you come down, they reach a loading, a resistance ratio of about 1.6 something. So if you look at 1.6, corresponds to loading of something like 0.92, 0.93, I guess. So at this point, they've reached a loading of 0.93 directly by resistance ratio measurement, which is something which seems shouldn't be possible based on our Vollmer Tafel models from Fitz and Green. Here's some data using the Dardic superwave protocol for loading. So let's see, here's the resistance ratio, which is, it's gone over the maximum, it's going down, it's going down, going down, it's reaching a little bit over 1.3 here. We go back to the curve, 1.3 corresponds to loading that's really close to 1. So here's the loading really close to 1 that's being observed. So here's another cathode which is reaching really heroic loadings. As it turns out, these days people can do this sort of more or less as a matter of course within the cold fusion field. I haven't been seeing that the electrochemistry literature has been interested in this particular bit of applied physics and so forth. But the question on the table is, how can the loading be so blasted high? So, for example, we know how Vollmer works. Vollmer brings the deuterium. We even know the rate at which deuterium is brought, and we have experimental backup for that. Tafel deloads, the deuterium on the surface recombines, forms gas on the top. So the question is there some reason in these experiments why it should happen more slowly, or Vollmer should happen more quickly? Namely, we got the model parameters for Vollmer Tafel. The model parameters don't give loading higher, but experimental data is giving loading that's higher. And this somehow seems to disagree with basic Vollmer Tafel. Vollmer Tafel's in the textbooks, so we think Vollmer Tafel ought to be right. So we got textbooks, we got experiments. What should we do? Should we discredit the experimentals? No. We wonder what's wrong. And so let's put it to the test. So Vollmer Tafel says Vollmer current, Tafel current in equilibrium. This gives us an absorption isocurrent. So there's not being agreeing with the new experiments, which is broken. Is Vollmer broken? Or is Tafel broken? Or are they both broken?
Or are you not at equilibrium?
Turns out the time for equilibrium is sort of fast relative to these experiments, so equilibrium is a pretty good assumption. So deuterium comes to the surface by Vollmer, And there's many experiments which show the rate. And I kind of tend to think that foamer is not going to be impacted by very much. Now, if you have different surface morphology, you can actually have an enhancement of foamer, probably factor 2 enhancement of foamer. But factor 2 is not going to make a dent in this particular problem. So I'm looking at taffel, and I'm thinking, taffel deuterium coming off the surface. I'm thinking, I think taffel's the one that's broken. Taffel being some more surface. People measure surfaces, and sometimes it has on the surface. But I'm thinking, what about inside the cathode? If I got grain boundaries, if I got internal, basically surfaces, I can have gas lead an internal surface, which basically means that a simple model for taffel doesn't distinguish between exterior surfaces and internal surfaces. And maybe that's the difference between the cathodes. So the idea is that Green and Britt's cathode would basically be a leaky cathode. You put your deuterium out, it's coming out through internal leaks all over the place. You got one of the cathodes like SRI used, maybe it's got all the leaks plugged, so maybe it's not leaky. So suppose we decide to take the most heroic cathode that anybody's ever found and fit the foamer taffel region curve based on the best cathode and say that I assert for that cathode, maybe there's no internal leaks. That gets me a taffel prefactor. So the best curve basically looks like this. If I plot taffel current as a function of loading, the highest loaded cathode that I'm aware of sort of goes along this line. Whereas the ordinary Green and Britt's leaky as a sieve cathode looks like this. And it's about 3.5 orders of magnitude difference in the taffel current. So the argument is you can get a resolution to all of this by saying in your average cathode, it leaks like a sieve. You've got something on the order of 3,000 times more surface internal to the leaky cathode than you have on the surface of the cathode. So if you make that kind of assumption, now you can resolve this. Basically, your argument is the cathodes that load really well are the ones that don't have internal leaks. If I want to model it, I might say, here's the normal surface taffel mechanism. The only thing is that the taffel current constant now will be much smaller than I've been using before. So this is outer surface, but I have to add this to keep track of the inner surfaces. And if I do this, then I've got an additional parameter, which is the inner surface multiplier, which is going to tell me how much inner surface I have. And I'm going to be able to understand the experimental results and deal with them. So the effect is huge. And basically, if you want to have your cathode load higher, you've got to get rid of the internal surfaces. Turns out that Ennio Frascati, Vittorio Violanti and his team have been studying this. So they've been working with foils that are between 50 and 100 microns thick. And you can see from the plot of the surface, you can see the size of the grains here. The grains are basically on the general order of the foil thickness. So by doing it, you've got a grain size that minimizes the number of internal surfaces. So they're roughly single crystal, each of these grains, sort of from one side of the cathode to the other, these foil cathodes. So they've studied the thermal treatment, the annealing, so they've got the temperature and they figure out what the maximum loading is that they can get. So they've optimized the metallurgy to maximize the loading. So they've been worrying in part about grain size for the reason I talked about. They've also worried about internal stresses as well. The takeaway message is that cathodes didn't load in 1989 in many experiments, basically because they leaked like sieves. Put your deuterium in and just have every which way come out. And that the ones that worked much better largely worked much better because the internal surfaces weren't present or weren't leaking deuterium. And in a sense, you can go a long ways towards getting high loading and seeing excess heat by taking care of this part of the problem.
So the deuterium part individual atoms are able to migrate in and out along the green boundaries. In other words, there's very free access in and out.
Yeah, you get 1 to 2 orders of magnitude increase in the effective diffusion coefficients due to what's going on within the green boundaries. So deuterium or hydrogen goes very, very much faster. Thank you. Other comments or questions?
It's the case that the deuterium that leaks internally, it migrates its way and disappears.
Has no problem getting out.
Okay.
All right. Well, we've come a long way so far. Our focus so far today has been trying to figure out what it is that you needed to do, well, how to think about the negative experiments and what it takes to get high loading. Now we're going to begin to shift gears. We're going to begin to shift gears for the rest of at least my part of the lectures here. And the thing we're interested in doing is to work towards a picture as to what's actually going on. Namely, so far we've been just thinking about electrochemical issues and macroscopic issues. But at some point, if we're going to have some new kind of physical process, we're going to need to know what that physical process is. So what I want to do is I want to change directions. I want to head in the direction of beginning to sort that out. Now, having said that, there's no accepted model for how this works within the community. Ideally, if you're in the theory business here, parameter space for theory is infinitely large. And if you make a theoretical statement, given the largeness, the hugeness of the parameter space, you're likely to be wrong. So what you'd like to do is you'd like to have the experiment tell you what's going on, in as much as what's possible here. So as a result, in terms of trying to figure out what's going on, I want to be guided by experiments to the exclusion of everything else as much as I can possibly do, or be guided to known physics issues as possible. I want to defer the new physical mechanisms going on as long as possible, which operation is going to mean we're going to defer that until tomorrow, but we're going to start getting closer to it. But we're going to need an ansatz of some sort. We're going to need to make at least one statement. And the statement that we're going to work with now, the ansatz, is that somehow D2 is finding its way to helium 4. What we're going to do is we're going to take Fleischmann's conjecture that deuterium's involved, that maybe somehow 2 deuterons are finding a way to do something interesting. We're going to take that as a very naive ansatz now. A little bit later on, we'll actually introduce something that could be viewed as being a theory, including Hamiltonians and mechanisms of matrix elements and so forth. But for now, we're going to be much less comprehensive. So if we take as an ansatz that D2 is responsible for what's going on, as it turns out, that already presents us with some gigantic headaches in the Fleischmann-Pons experiment. So it turns out it's not going to be easy to get D2 to come together. In fact, we're going to conclude that D2 as a molecule-like object simply can't exist in palladium deuterite, in bulk palladium deuterite. And that we're going to need to do something to bulk palladium deuterite in order to make any progress on this problem. And this is going to lead us to some connections with the experiment that are highly natural. So the place where we're starting actually is with helium and metals. You're going to say, well, this seems like a very weird place to start. But as I hope you'll agree with me, it's the right place to start. So there's something called embedded atom theory in the literature that includes some intuition way of thinking that will be extremely helpful to us. So what had happened is in the 1970s, people have been doing models where they work with something called jellium. So jellium is this non-existent material where you send a uniform ion background and you put electrons in, and gives you a quantum mechanical problem you can solve. People are working on it, solving it, and getting interesting answers. And then somebody else said, well, what happens if we take an atom and we put it inside of jellium, which gives us a theoretical problem that we can solve. So people have been studying that and focusing in large part on hydrogen, helium, and also rare gas atoms, because they're theoretically interesting problems. Everything changed when, in this paper, these physicists basically figured out that all of this idealized calculations and so forth actually connected with experiment in a highly non-trivial way. And the conclusion was is that if you assumed that basically the potential was the embedding energy, and there's plus a atom-atom repulsive potential at close range that's weak, but if you're not at close range, then this works pretty well. Let me show you a plot from the paper. So here's a plot for modeling helium scattering, and the potential is involved. So there's some experimental data and some very complicated theoretical curves that have been developed as well. This interesting black line that seems to be reasonably close to experimental data is the result from this embedded atom picture. And it turns out, let's see in a moment, this is really simple. So the quantum mechanical problem, the interaction potential of two heliums can be applied. Basically, it's a quantum chemistry problem. You've got to burn up a fair amount of computer time to solve it. But what this curve does is said, let's take an embedding energy, and this is a later version. So you see it's basically linear in the electron density. So this curve here is essentially saying that figure out what the electron density is to the helium that you're hitting, use that to figure out the potential, and it compares pretty well with experiment. So you basically don't have to do much work at all, and you get a really good answer. They published this, and people looked at it and noticed and said, this stuff looks like it could be important, and it's important for us. So that's a basic. So I'm thinking that the associated quantum mechanical problems are a mess. If all you've got to do is figure out the embedded energy to get an estimate for the potential, then you can take problems that are really tough and you can make them simple. Plus, it gives you an intuition. So this was, in my view, this was a major advance in understanding and modeling. And we're going to be interested here in the understanding, and we'll be using it for modeling also. A little bit later on, tomorrow, we'll be interested in these helium diffusion of palladium. Today, I'm going to pass on that. So here's helium. What's the embedding energy look like for hydrogen? Well, here's from one of their papers. It goes down and comes back up. That's interesting. That's really interesting. So hydrogen and jellium has a certain electron density that wants to see. And it's also an attractive potential that it's going to be, if it finds that electron density, it's going to want to sit there. But it minimizes its influence by finding that electron density. And that's big. So that's, if you like, the message here from embedded atom theory. So the ideas are relatively simple, and we're going to want to use them and exploit them. So here's a close-up of the hydrogen embedded energy curve. So it goes down, it's got its minimum, and the minimum occurs in this particular model at 0.069 electrons per cubic angstrom. And so those are funny units, 6.9 times 1022 electrons per cubic centimeter. Now that's the electron density that in this picture that hydrogen wants to see. And then we can even see that it increases roughly linearly above that magic optimum electron density. Let me pause for a moment. Are there comments or thoughts or questions so far? Anyway, you getting the gist of this? And this is really powerful if it works. You can take really hard problems and understand them trivially. So I'm interested in molecular palladium hydride as the first test of it. Basically, I want to see if it works. So we have this embedded atom model that says hydrogen near atoms or near solids and near surfaces. It cares about the electron density. It's looking for just the right electron density. So let's take the molecule palladium hydride as palladium hydride, palladium deuteride as a way to to start. So the molecule's been studied. Here's hydrogen, here's palladium. The distance between them is 1.53 angstroms. And it's been studied using quantum chemistry codes. The theoretical minimum agrees with the observed minimum. It's interesting, palladium, the ground state of palladium is sort of a rare gas type configuration. So it's like you've got a hydrogen atom, which is spherically symmetric, you've got a palladium atom, which is sort of spherically symmetric, and they come together and they make this, this object, this molecule. So we calculate the electron density. So what I've done is I've taken I have a relativistic entry thought code, which I wrote years ago, and I calculate palladium and calculate the electron density. You're welcome, have a seat. You have electron density, and at 1.53 angstroms here, we find that the electron density of palladium turns out to be 0.069 electrons per cubic angstrom. So let's remember that, go back and check it against the minimum for the embedding energy. So the 0.069 electrons per cubic angstrom. They say, fantastic, this works. So we're getting consistency at this level. Of course, getting such exact consistency between the factory thought calculation and embedding energy from this model, having it be spot on is coincidence here. There are other embedding models for hydrogen that give minimum a little bit different electron densities. But what this is telling us is that the basic picture at least seems to have some predictive capability, as well as being intuitionally compelling with respect to intuition. Let me pause for any questions, thoughts. Are you impressed yet? You're supposed to be impressed. You're a tough audience. Okay, so let me think about the palladium hydride crystal. So what's the story with hydrogen in palladium hydride or deuterium in palladium deuteride? So here's what the lattice looks like again. We recall that it's an FCC face-centered cubic lattice, and we've got checkerboard at this level, shifted checkerboard here. So palladium's on black, deuterium's on red, and so forth. So to use embedded atom theory, all we have to do is figure out what the electron density is due to the palladium atoms. So what I've done is I've taken a simple superposition model. I've said each palladium you can view as being a free space. You add up the electron density due to each one individually, and you get a curve that looks like this in the 1-1-1 direction. So the 1-1-1 direction is sort of going like this. So this guy here, this position here would correspond to the middle. So this is the octahedral site, and the tetrahedral site would be here and here in this curve. So what we see is that the electron density is lowest at the octahedral site, and at the octahedral site, in my calculation, it actually looks like it's close to that magic number that hydrogen wants to see. At the tetrahedral site, the electron density is a little bit higher. And so if we look at this and we recall what the embedding energy for hydrogen looks like, we come to the conclusion that hydrogen is going to want to sit here. But this will be a significantly higher energy, so that hydrogen is not going to want to sit at the T sites. That's in agreement with the experiment. So although this one looks a little bit lower than 0.79, the better calculation I have has it being at 0.079 for the minimum of the octahedral site, a little bit above what hydrogen wants to see according to our embedded atom model. The T sites are a little bit higher electron density, which is sort of much too high for hydrogen. And this gives us an intuitive understanding as to why hydrogen and deuterium plug into octahedral sites. Turns out it also gives us some intuition that says that palladium ought to have a high solubility for hydrogen because it's got the right electron density that hydrogen wants to see, whereas some other metals aren't going to be as well matched. For example, here's nickel. The electron density of nickel with the same kind of model, same kind of approximation. The minimum is here. which is even higher. So here's the electron density that hydrogen wants to see. We're sort of up a factor of two too high. So what this tells us is that because of this, hydrogen's not going to like nickel very much. So the solubility of hydrogen and nickel is going to be low. And that agrees with the experiment. So we calculated 0.132, or almost, electron density almost twice too high. We can actually look at the phase diagram to verify this. Here's the phase diagram for nickel. You start to load, you get a miscibility gap. Here's the miscibility gap at room temperature, and then you go up. So the question is, what's the pressure here? So here's the pressure in megapascal. So say, well, what the heck is 400 megapascal? I'll give it to me numbers I can understand. So if I go convert 400 megapascals, which is here, into atmospheres, it's about almost 4,000 atmospheres. So we recall that palladium breaks the miscibility gap somewhere in the general neighborhood of 100th of an atmosphere. So this is a much higher pressure that's required. So we see that the nickel's much, much harder to load. It can be loaded, but you have to do a lot more work to load it. So here's the takeaway message. So takeaway message is that our embedded atom model seems to be giving us intuition as to how hydrogen loads. Hydrogen works next to atoms and surfaces and so forth. It gives us an awful lot of intuition as to how these systems work. And what used to be something that's conceptually maybe a little bit complicated, now it's starting to look much simpler, much more understandable, much easier to understand. Comments or questions?
You showed the curve for phase center Q. Other phases, crystal forms, are there better?
As it turns out, we're going to see a crystal form that's much better shortly. But we don't have all that much choice for bulk nickel hydride or palladium hydride if you make it near room temperature, either by gas loading or by electrochemical loading. We tend to produce FCC phase center Q nucleus. Other comments or questions? Okay. So now, in our picture, if we wanted D2 to do something, we need to get D2 into the lattice. So now we're going to begin thinking about what's happening with D2. And what we're going to do is we would like to use embedded atom theory to get some intuition. What we're going to find is that embedded atom model things are a little bit more complicated. The basic idea is that helium and hydrogen work particularly well in embedded atom models because the polarizability is small. But molecular H2 and D2 has a very large polarizability. So that means that we're going to have to include that in our thinking. So let's begin by looking at the embedding curves. So what I want to draw your attention to first is for H2. And here's the embedding curve in one model for H2. And it's a lot like that for helium-4. So you put helium-4, helium-4 doesn't like electron density. You put H2, H2 doesn't like electron density either. And so you scratch your head and say, well, obviously if you've got any electron density, you're not going to have H2. But if you allow there to be some separation between the hydrogens, you get different shaped curves. So this curve, actually this curve is for H2 with a separation of twice the 0.74 angstroms of vacuum D2. And this other curve, this one is for the two hydrogens with infinite separation. So what you see is, depending on what electron density you have, you've got different minimum energies depending on what's going on. But it also tells you that once you reach a certain electron density, that the hydrogen would much rather be separated than look something like a molecule. So there's an extra degree of freedom in the separation, and there's polarization effect. But generally, it suggests that we ought to be able to arrange for an H2-like molecule within our material if we lower the electron density. So that's what I want to begin thinking about. So I want to start thinking about it. I'm going to put the molecule now next to an atom to see what happens. If I put it next to argon, I find a minimum here. I get a weakly bound van der Waals complex where the molecular hydrogen is binding as a molecule now to argon. Now, if I look back at the embedding curve here, embedding curve says, if there's any electron density, then the energy goes up, so I shouldn't bind at all if embedding energy with the whole story, but this is clearly binding. The question is, why is it binding? Well, it's binding because there's a dipole polarization, which is giving an attractive term. So this is a van der Waals kind of interaction. So you say, well, argon's not very polarizable. That's true. That's why this is very far away from the atom and very shallow well. So I'm thinking I've got some understanding of the basic embedded atom model. If I augment it with a polarization attraction, then I can use it and I can understand it. So now I'm going to think about H2 binding with palladium. And as it turns out, this by itself is an extremely interesting problem in the chemistry literature. For many years, it was thought that you couldn't have H2 bind as a molecule, H2 with an atom, that it would split up and form a bunny ears configuration, sort of like an H2O. And this is hotly, well, it wasn't hotly debated, the textbooks had that you couldn't do it, period, until around 1980. It turns out palladium hydride 80H2 was one of the very first examples of the prediction with a quantum chemical calculation that H2 could bind as a molecule next to an atom. So when further work showed that this was true, but it was one of a class of material they're called sigma-bonded dihydrogen complex materials. So there's something in the neighborhood of under 200 substances known where molecular hydrogen can bind with a metal atom in a form that looks something like a molecule. And this one was one of the very first cases. Anyway, the equilibrium separation is 1.67 angstroms. The HH distance is 0.81 angstroms, which is a little bit bigger than 0.74 for vacuum H2. So these famous people did basically a field opening calculation of a relativistic model of palladium and hydrogen, molecular hydrogen bonding together. And what they found is that the minimum energy for this particular system is in fact this configuration where H2 is coming next to palladium as a molecule. That's really, really interesting. The bunny ears configuration is over here, and it has slightly higher energy, but the sigma bonded dihydrogen complex is the minimum energy configuration. So people have done a number of calculations of binding curves. Here's one example. Here's sort of parameterization where I can visualize it. So in this case, the binding energy is about close to 0.8 eV. Turns out there's not agreement as to what the binding energy is in different calculations. You get numbers between 0.22 and about 0.76. This is a problem that, if you happen to have quantum chemistry code calculations, is strongly encouraged. Okay, so involved, and I think I'm going to pass on some of them. But the palladium, it binds with the molecule. The palladium has some polarizability, which leads to the attraction, which gives you reasonably strong binding, so it's not a van der Waals complex system. Here's the case of nickel hydride. I was arguing that nickel is sort of the kid sister to palladium in this case. And so we can look for the same H2 nickel minimum energy. And in a sense, there's a minimum here for singlet A. Basically, this is a singlet version of the nickel molecule binding with the H2 molecule. It's got a minimum. Turns out that the linear molecule is the lower energy version. The HH separation is much larger here in the case of nickel than it was in palladium. So nickel's not doing as good, and in part from my point of view, it's because nickel's got a much stronger polarizability. And if you think about it, the polarizability, in this case, I guess I'm thinking quadruple polarizability. This state's 0.8 eV above, whereas for nickel, you've got other states that are very close. And so there's a much bigger quadruple polarizability for nickel. So palladium is a little bit special, and H2 is willing to come up and be next to H2 and minimize its energy as a molecule. So that this is encouraging with respect to trying to get D2 into palladium deuteride, because palladium is sort of set up to be willing to be happy with them either H2 or D2 molecule next to it. Okay, let me pause and entertain questions. Comments or questions or thoughts so far? Okay. So now I'm going to try to see if I can arrange for D2 to be in palladium deuteride. So how does it do? The issue has to do with the electron density. We've seen from the PD molecule that the electron density from the PDH2 molecule, the electron density that the H2 is happy with in that case is 0.033 angstroms per cubic 0.033 electrons per cubic angstrom. And that's more than factor 2 below the minimum molecular density in palladium deuteride. So the question is, I've gotten ahead of myself. So let's review that calculation. Here's the molecule, H2 molecule, here's palladium. Here's the electron density of palladium. And the separation is 1.67 angstroms, so we look at 1.67 angstroms, and it's 0.033 electrons per angstroms. So now we know the electron density that the molecule is happy with, that the H2 is happy with next to palladium. So this gives us an electron density to shoot for in the solid that we'd like to have be present. And when we look at the electron density due to the palladium in PDD, then the minimum is 0.079 in the better calculation than this one. So it's more than a factor 2 too high. And that means that the molecule is not going to be happy in palladium deuteride. And we can conclude from this that D2 can't exist in palladium deuteride, as was known in the literature. The people doing solid state calculations understood this back in 1989. We can see this from calculations which tell us how the H2 molecule falls apart when we increase the electron density. So if we go to the molecular H2, there's a symmetric combination of orbitals, of electronic orbitals. There's an anti-symmetric combination of electronic orbitals. And the symmetric combination gives us the singlet sigma Gerada state, which is binding. And if one of the electrons is in the anti-symmetric orbital, it gives us the anti-bonding state. So if we have an electron in the anti-bonding orbital, it pushes the two protons apart. So what that means is that if you put your H2 into jolyon, as the electron density goes high, there's a lot of electrons around. The electrons tend to occupy the anti-bonding orbital of H2, which pushes it apart. And you can see that in the H2 and jolyon case here, that in vacuum, you get a minimum separation of about 0.74 angstroms. If you put it in jolyon, and jolyon went 0.063 electrons per cubic angstrom, what you find is that the minimum separation is much larger, and basically the thing's fallen apart. This electron density is basically the limit at which the molecule can't hold together anymore. And we see that this electron density is less than the electron density expected in palladium deuteride, which is basically why the molecule can't survive in the crystalline palladium deuteride. Okay, let me pause. Questions, comments, or thoughts? So the solution to it is we've got to lower the electron density. Palladium deuteride by itself isn't going to work. We're going to have to modify palladium deuteride. So what we're going to do is we're going to take out a palladium atom at one site. We're going to make a mono vacancy palladium. So this is again the face-centered cubic structure shifted relative to the pictures we've shown earlier. And I've taken out one of the palladium, so I have a hole here. So the question is, what happens now in the vicinity of a vacancy? So the deuterium atoms relax towards this vacancy. They relax a little bit because they're looking for the magic electron. So here's a way to think about it. So here's the site of the vacancy. The electron density, there would be an O site, or I'm sorry, there would be a T site somewhere around here in the TTT direction. If we go a little bit away from the vacancy, we get down to electron density of 0.033. And this was the magic electron density that the molecule wanted to see next to palladium, with H2 wanted to see next to palladium. We can suspect D2 would like to see this electron density next to vacancy. So this problem's actually been studied. It turns out it was first proposed back in 1989, 1990. Somebody, I meant to include the citation, I've even forgotten what it was, and I feel very bad about it. My paper cited the paper that was actually first proposed. My proposal, this was independent 3 years later. So the question is, what can we do? So I'm thinking about it. I'm plotting the electron density in the different directions. You can go this way, you can this way, you can go this way, and around the vacancy, the electron density goes down the slowest in the 1, 0, 0 direction. So it's sort of, on the checkerboard, it's going from that black space nearest red space is that direction. So in this direction, here's a normal octahedral site with no vacancy. If the vacancy is present, then in this calculation, density functional calculation, the hydrogen moves down a little bit. And people have done neutron scattering experiments to see where the location is of the hydrogen and deuterium, and they find that it moves like 1/10 of an angstrom or so. So what this tells you is that the electron density is close to the optimal electron density for hydrogen, very near the normal octahedral site when you've got a monovacancy. And these problems are studied in the literature. I've started going very quickly through it, picking out some highlights. The resulting picture is, here's the electron density from my simple model, superposition model without a vacancy. Here's the electron density, here's the O site. If you have a vacancy, then you get to an optimal electron density a little bit further in, which is calculated, which is observed. And then you get a position right here, you should expect a D2 site to be the potential site for a D2, the D2 could form, because this is where the electron density is roughly right. Here's a density functional calculation by Renu Charo. Basically, he's looking in the 111 direction. No, he's looking in the 100 direction, so he's looking along here. Here's the site of the vacancy. Here's the site of the vacancy. So here's the energy of the D2 molecule, and it comes down as you go in. So the idea is that starting here, going in this direction, here's where I wanted to see the D2 show up. So he's finding a minimum in energy. This is the DD separation, so this is close to 0.74, it's about 0.76 or so. There's a few electrons around. There's a little bit of separation. As it moves in away from the vacancy, it goes up, but then a caging effect brings it back down. So in this region here, you've got a DD distance, that's an HH distance, which is about 1.05 angstroms, which is, it's interesting. In the molecules, in the signal bonded dihydrogen complex, this would be considered to be a sort of a success H2 next to a molecule. So in this case, it's a caging effect. So this was sort of one of the very first modern density functional calculations to show the effect I was interested in. It turns out I like this calculation, but I'm looking at the distance between here, and I'm saying, well, this molecule is very, very strongly bound. I'm kind of dubious that it can be bound so strongly. I was playing with some models where I was using the embedded atom model augmented with the polarization attraction model. And I think this is probably closer to what things look like. I think rather than coming down in volt, I think they come down by about 200 millivolts or thereabouts. And then the minimum is over on the other side of where Lou is getting it, but it's sort of qualitatively similar. There's a caging effect going on there too. So DFT results intriguing. Binding energy seems to be too large and slow. So now we turn to the literature, because the literature is very interested in these kinds of problems also. And in the literature, there's a lot of calculations where people bring molecular H2 close to a surface, a flat surface of palladium or palladium hydride. And what you see is that here the mean separation is 0.74 angstroms. So you've got a molecule that's above the surface. And as the molecule comes down, gets close to the surface, the separation increases. So here the separation is increasing. And then it goes here, you end up having the hydrogens break apart and go into the sites where they're finding electron density which happy with. So the quantum calculations in literature shows this effect and shows it clearly, cleanly. Even gives you these contours of how many electron volts worth of binding energy that we get from it. It turns out that the closest analog to the D2 molecule inside the vacancy that I found in the literature is this. There's evidence for H2, there's experimental and theoretical evidence now for H2 as a molecule bound on the surface of PD210. Actually not PD, it's PDH. So the idea is that you come in and there's this spot where you've got an energy minimum here. And I've been trying to figure out how best to visualize it, but it's basically the molecules above one of the palladium atoms, a little bit like in the PDH2 molecule. What's interesting here is that the H2 doesn't fall apart like it does in the other calculations because it's assumed that there's hydrogen fully occupied on the sites where the hydrogen of the molecule normally might go. So whereas normally it breaks up because there's available octahedral or near surface octahedral sites, in this case for the PDH, all of them are blocked. So the molecule doesn't fall apart. And there's an energy minimum where it's sitting here. And that's really, really interesting because of this, because from experiment and from theory now, we know the molecule, we know the separation, we know the binding energy. It's bound by roughly 270 millivolts, which is basically the number I was looking for, but it requires the other sites to be occupied by hydrogen. So I'm thinking that this is the closest analog to the D2 state that I'm proposing is responsible for the effects in the functional bonds experiment in the water vacancy. Takeaway message. Well, the takeaway message, the D2 can't form in palladium deuteride bulk because the electron density is too high. So we want to lower the electron density. So if we can remove a palladium atom, we can get low electron density. And so we've looked at it theoretically, and in the literature, there's an analog. There's a surface state for fully loaded palladium hydride, which sort of, is sort of a perfect kid sister to what we need with the binding energy that's right in the right range for what's needed. Let me pause and catch my breath and entertain questions. Thoughts? Mind you, to prove this, there's for single bonded dihydrogen complexes, people use NMR to tell the distance between the hydrogens to verify the existence of the molecular D2-like or H2-like complex. The same approach could be used to determine whether this is true in these systems. So this doesn't have to be one of these theoretical things. If there were support, these experiments could be done to measure whether a molecule in D2 or H2 exists near a vacancy. And now,
So if I'm understanding correctly, it seems that for this to work, we need vacancy in the middle. How do you get one that?
Let me have my first connection with the flashing bonds experiment. Actually, there can be a few connections here. In the next few slides, I'll have a great answer to your question. So let me begin by saying, suppose that we find a way to make the vacancies, then how does the loading and the generation of molecular D2 work? So I'm going to start out by assuming they exist, then I'm going to come back and say, how do we make them? So if they exist, then for the D2 to form, all the other octahedral sites in a vacancy have to be occupied. So you need some loading to make that happen. So I've put together a thermodynamics model to model the formation of this species, given the need for occupation of the other octahedral sites in a vacancy. And what I find is that you need to have a loading above about 0.83, 0.85 to generate significant amounts of the molecule. And possibly you recall these numbers for something like the numbers needed for excess heat in studies at different laboratories. That you need a loading of 0.83, 0.85 or higher to get excess heat. So a simple explanation of this curve is that you can't get excess heat down here in the Fleischer-Pons experiment, basically because you've not filled up the other octahedral sites near one vacancy. So you can't form molecular D2. So basically, it seems to me that there's a real possibility of consistency between this theoretical picture and the experimental results from the early experimental efforts to cause excess heat. So the takeaway message is that choosing the ansatz that we're going to go from D2 and make helium-4, the D2 is involved, we seem to have the possibility of making a connection with the one of the loading requirements observed in the experiment. Questions or comments about this so far? So what about making vacancies in palladium? So this is an interesting problem. It's also well studied in the literature, and the answer is really interesting. It's very much unexpected. So your average bar of palladium contains vacancies, and depending on how it was treated, different amounts, from a low of like 10 to the minus 9th or something to a high of about 10 to the minus 3 or thereabouts. The vacancy and defect concentrations following the loading through the phase transition from the X-ray data I showed you earlier today, those numbers could be as high as 1% level vacancies. Mitchell and I got together and we were thinking, why not use electron beam bombardment to make vacancies? Mitchell described yesterday how we went over to the high voltage center and made some, and actually made quite a few of them, and then watched them decay after about 8 hours or so to the saturation level. And the saturation level is between 1/10 and 2/10% vacancies. You might say, great, we got vacancies. Sadly, I look at vacancies at this concentration and say that's way too low to be relevant to this problem. So I've done various levels of modeling, and according to my models, this just isn't going to hack it. So the idea is to try a more subtle approach. The more subtle approach is to say that let's look at the thermodynamics of the vacancies at different loadings. So if you start out with pure palladium, the literature value for the vacancy formation energy will be somewhere near an electron volt, maybe 1.2 electron volts or so. When you start loading palladium, every time a palladium, a hydrogen or deuterium gets next to the palladium, the vacancy formation energy decreases by roughly 200 millivolts. So if you have enough hydrogen or deuterium, you can stabilize the vacancies. In fact, at a loading of 1, you make the vacancies be energetically favorable. They're preferred thermodynamically. As it turns out, sometime in the early 1990s, I recognized this. I thought, man, it would be really fun to make some vacancy phase material if you could get it really highly loaded and heat it up so vacancies could diffuse. But it turns out somebody else is thinking along those lines, as I'll discuss shortly. But there were models available in those days for the vacancy formation fraction for the thermodynamics. And if you exercise the models, you generate these curves. So it basically says at room temperature, which is near here, at loading of about 0.95, you can get to like 25% vacancies. So this is good, but it's not good, and it's not good because the vacancies don't diffuse. But I'm of the opinion that this 0.95 number for the formation, the threshold for formation of this very large fraction of vacancies, is connected to this requirement seen at SRI, that positive results were seen when the loading reached a level of 0.95 or higher, and at lower loading fractions, the excess heat was not observed with very much regularity, reproducibility. So I think this vacancy formation threshold is responsible for the observed loading requirement we talked about last time. Pause for brief comments and thoughts. Okay, so Fukai, the very famous Japanese hydrogen and metals guy, he was looking at the same curves, and the difference between him and me is that he's a mainstream scientist with a budget. And we, of course, working in Cold Fusion, have no budget to do pretty much anything. So they took palladium hydrogen and very high pressure and heated it up, gave it enough time for the vacancies to diffuse. And what they found is that a new structure is made with the vacancies in 1 out of every 4 palladium locations. So some people refer to this as the Fukai phase. Fukai refers to it as a superabundant vacancy phase, but it's basically you can think of it as palladium 0.75H in this particular case. So they produced it, and when the hydrogen goes out, the structure, lower density palladium structure is stable, and that's really interesting. So I'm of the opinion of the inflation-Pons experiment that it's this structure that's the one that's interesting. It's got a huge number of these vacancies, so there's lots of places to host a molecular D2, and it's stable. Now the issue is the diffusion rate. So the diffusion coefficient for the vacancies is low. So as a result, at room temperature, if you were to wait 10 to the 6 seconds, you'd end up having a vacancy diffuse about 1/10 of an angstrom, which basically means that you can make the vacancy phase lattice in electrochemical, in gas loading experiments near room temperature. It's just that people tend not to be patient. You know, in this day and age, people, when things happen fast, you're not willing to sit around for some number of thousands or millions of years to wait for your lattice to become a Fukai lattice. So, in the old days, we would have waited. This brings us to an important connection with cold fusion experiments. The co-deposition approach to excess heat was really pioneered by Mitchell back in 1989. We didn't know about it at the time. Schwach published a paper in 1991 showing rapid onset of excess heat flow in co-deposition. So the thing to think about is that Fleisch and Pons experiment, the cathode size that they were using, you should be able to load them in some number on the general order of an hour, a few hours. But Fleisch and Pons would be waiting a month on the order of a month before seeing excess heat. So the question is, what's going on during that month? When Schwach has the results, they're seeing an excess heat effect in tiny minutes here. So here's half an hour, here's 1 hour. So now you have the possibility of doing an experiment in the order of an hour rather than in the order of a month. So this is co-deposition. So I'm scratching my head thinking, so what's this all about? The basic idea is that you want to form a Fukai phase. So the Fukai phase doesn't form generally in the bulk because the vacancies don't diffuse. But on the other hand, if you co-deposit palladium, so you put, in this case, you put palladium chloride into the electrolyte, run the electrochemistry, the palladium exists as a positive ion in the solution, and it deposits on the cathode electrochemically, sort of the same way hydrogen and deuterium does. So once you co-deposit it, you're making new material, but if you do that at high loading, the ground state lattice is the Fukui phase lattice. So your co-deposited palladium, if you do it under conditions of high loading, is making vacancies. And here you're seeing excess heat form under conditions where you would expect the vacancies. So I'm of the opinion that those co-deposition experiments are really important because they're conditions under which you generate the vacancies. And it supports the general line of argument that what's going on is you're trying to make the D2 molecules. The D2 molecules aren't going to form unless you've got low electron density and it requires vacancy to do it. So the conjecture here is that co-deposition is making Fukui phase. So after Schbach's experiment publication, a lot of people tried replicating the Schbach experiment to see excess heat, and they basically came away without very much luck. Part of the issue is that Schbach didn't explain much about the protocol that he used. So in the protocols later on, the co-deposition done, for example, by Pam Voss of Spadewar, a colleague of Schbach, they did low co-deposition of very low current density. And so when that protocol was tried to see excess heat by others, it didn't result. Now, Pam was looking for charge emission rather than excess heat effect. But for example, Dennis Craven's done Sleds and others tried the Pam Voss's protocol to do excess heat, and nothing happened. No excess heat was seen. So Dennis Letts, to his credit, he said, well, I wonder what's wrong with it. So what's wrong is you've got to get the concentration, the loading on at the time when you're doing your electrochemistry. So he cranked up the current density and found that the co-deposition gave a very poor surface, was flaked off. So he said, I need a good surface, so how to do it? So he said, let's back down the concentration of palladium by a factor of 25 to 40 or so, and crank up the current density. And when he did that, then the co-deposition led to a stabilized layer. And what he saw was excess heat sort of immediately after the co-deposition. So this is a version of the Schbach co-deposition approach, but with a different protocol. So this is sort of the Letts modification of the Schbach protocol. Mel Miles had luck with this protocol in his experiments. He got some of the highest excess heat from co-deposition that he's, or in that round of experiments that he had seen. Question is do we have a good way to test to see if we've made vacancies? And X-rays would be good, other methods would be good, positrons would be good. Thermal desorption seems to be an effective route. So Fukui and colleagues, they worked with some Fukui nickel hydride, and when they did thermal desorption, so this is down on the axis, not and so here's the desorption temperature. So here they see the hydrogen coming out of the bullet, but here they get two features that are not present in the absence of the vacancy phase. So these features are basically the appearance of these features on thermal desorption spectrum tells you you've got your vacancies around in the case of nickel. My thinking is that palladium will be similar, but I haven't got some data at the moment to show that. Fukui found some nickel that had been electroplated that had sat around for a large number of years, 32 years. So the idea is that the vacancies are stable. Thermal desorption done on it gave these two features, which Fukui food is being comparable to these features, meaning that the Fukui phase, that the vacancy phase was present and stable for a long time. So the thinking is in Fleisch-Plann's experiment that co-deposition happens inadvertently through inadvertent co-deposition. So at SRI, they do an experiment, they cycle cathodic and anodic. When they're anodic, they strip some palladium into the electrolyte. When they're cathodic, it loads back down. And at high loading, it would form Fukui phase near the surface. In Fleischmann's experiment, he had a reference palladium reference electrode that was unprotected. So if it corrodes and puts palladium into the electrolyte, it would make a thicker region of palladium than other people were working with. And I'm of the opinion that that's the reason Fleischmann-Pons' experiments gave lines of seed and everybody else's. The surface of the Fleischmann-Pons cathodes were analyzed by a team of NRL, and they found surface evidence for platinum. So if you think platinum comes from the anode and goes on by co-deposition, extending over 1,000 angstroms. So this is the size of the surface region of Fleischmann-Pons cathodes that you might use active, and the SRI would be a thinner surface. So the idea is that the interior, you've got bulk palladium deuteride, which you might use inert. You've got the electrolyte, and then you co-deposit a thin surface layer. The Fleischmann-Pons experiment, I'm of the opinion, is this co-deposit surface layer, which in Fleischmann's own experiment can take about a month to form. That's where the action is. Let me pause. Your thoughts or comments? I'll be wrapping up very shortly. Questions or thoughts or comments so far? So the NRL folks did an experiment at a synchrotron. So they took a palladium cathode and they loaded it, and they had a synchrotron coming in to glance off the surface to look for the lattice constant near the surface. Now, we recall the lattice constant for both palladium hydride goes from about 3.88 angstroms to about 4.07 angstroms at high loading, 3.88 for unloaded material. So, so in the SRI experiment, here's high loading, and you get a loading which is, well, you get a lattice constant, which is in the general neighborhood of 4.08, which corresponds to very high loading, either at or slightly above unity. And during the talks they gave, the lattice constant tended to go down. And then I'm not 100% sure whether that's the effect that we're seeing here. They talked about it at the conference. I think this might be it. And I'm trying to think to myself, thinking, what's going on there? They argued that possibly they were seeing a phase change happen at a very high loading. And this is the variation lattice parameter in PDH and Fukai's experiments. So for example, in an experiment like this, they start with the lattice parameter, it's very high. Now at high temperature, the lattice expands a little bit. So instead of 4.08 and 4.19, they're 4.12 here. But when the Fukai phase forms, the lattice parameter comes down. So the presence of palladium vacancies means that the lattice is a little bit more compressed. So it goes from here to here. So you're getting a reduction in the lattice constant of something like 0.06 angstroms. And here you're getting a reduction in the lattice constant, something a little bit less than that. But I'm wondering whether what's happening here, and maybe might be happening in other experiments, is that perhaps instead of having things happen by co-deposition, perhaps there's a way, if the loading's high enough, for you to actually generate a spontaneous phase change. If you think about it, if the loading gets to be high enough, you've got some free energy around that can drive a rearrangement of the lattice. You have enough energy to be able to make things happen. So perhaps you can induce a phase change at high loading, and maybe there's the beginnings of evidence for that in the NRL. So anyway, a long story. We've got to summarize for today. We've got a way to measure resistance ratio. We can focus on the resistance ratio to tell our loading in experiments. We're interested in why getting high loading is hard. In order to understand that, we looked at the Bowman-Tappel model. We found that basically cathodes are hard to get high loading in because of leaks. You can interpret the experimental data that way, and it seems to make a lot of sense. So in order to do experiments that maximize the chance of seeing excess heat, you've got to get the high loading, which means you've got to get rid of your leaks. We talked about embedded out models, ideas for hydrogen helium, which gave us a way to understand plate, hydride plate, and deuterite very simply, loading the octahedral sites and so forth. They found D2 can't form in both plate and hydride, because electron density's too high. You need a vacancy. We examined the possibility of getting D2 or H2 to form vacancies. It's promising. There's an analog in the literature for the H2. And we propose that the observation, the excess heat increases with loading above the threshold loading is consistent with the D2 occupation near the vacancies. We've also talked about the possibility of making the vacancies through co-deposition, perhaps phase change, and the connection of the Foucault. So that's what we did, and I'll finish up with my standard warning. Any final comments or thoughts on the unit? So if not, Mitchell, we're going to have a bio break. Mitchell will do stuff tomorrow. I have a dentist appointment in the morning, so I might be here a few minutes late. Maybe if I don't get here until Mitchell, I might be starting tomorrow.
I'm not sure I understood everything you said about the leakage and the increased surface area. On one hand, it seemed like you had to have the increased surface area, and you had to have free movement of the deuterium in the and near the surface of the cathode. But on the other hand, you have to have minimum leakage in order to get the loading. Am I confusing two different things there? Or?
So I'm not sure. The basic question on the table is, why in the world was the loading so low in the literature relative to the very high loading seen in the cold fusion experiments? And so the interpretation is, the only possible interpretation from my point of view, is that your average cathode back in those days was an extremely leaky cathode. So with internal leaks. So in the Green and Britz experiment, they would load their cathode, they'd do a good job with the electrochemistry, but because their cathode leaked like a sieve, what would happen is their maximum loading would be limited to too low to be interesting. So microscopically, you need internal surfaces, plus you need channels or grain boundaries to go between where the leakage occurred internally to get the gas out. So that's a basic picture. If you increase your crystal size internally, which is what Vittorio does, and reduce your local stress, then you can increase the loading, has been found systematically by that group. If you make your crystal size too big, then it becomes very brittle. These things fracture, split open like an overripe banana, in order to use a phrase of McCooley.
Thank you.
Is it the case that, say, somebody who's not all that familiar with what they're doing was trying to get this high loading and tried to do it maybe a little faster than they should, and would that tend to break up your crystals and cause?
In my view, if you do anything wrong, you're just done.
Yeah.
If you load too fast, your cathode's going to, you're going to have that discontinuity go through. You're going to destroy the internals of your crystal. It's going to look very ugly, and the solubility is going to be low. If you're not super clean, turns out the surface of the cathode is like a vacuum cleaner. Any impurities in your system collect there, and if they collect there, they can block the loading. So you basically have to do everything right to get the high loading.
And people who were new to it, say when they were...
This was only understood sort of intuitively by a small number of people back in 1989.
Yeah. These are likely things that contributed to the negative results early on.
Yeah, in general, and early on, the majority of folks doing these experiments didn't understand the experiment so well, mostly because there's no information out about it. The notion that you needed a high loading apparently wasn't common knowledge. If you look at the literature, a small number of the papers that are relevant even bother to mention the loading at all. Of the papers that reported negative results and that measured their loading were worried about the loading. The loading wasn't all that high. Certainly wasn't high enough to be interesting or give you a high probability of getting a positive result. And there are other issues with respect to getting experimental work that we haven't talked about. You'll also might address in these papers.
Mitchell's going to present after lunch more, or should I stop this?
Your choice. I'm stopping presenting. It's bio break time in as few minutes as we can manage to take bio breaks and so forth. We'll reconvene. So, Mitchell's done. Okay.
So send an email.
Good.
I'm sorry.
I'll send you the papers this evening.
Okay, the first time I forgot to put IAP in the subject line.
It doesn't matter. We're very close.
Thank you.
To remind me of why we know.
You coming back?
I mean, it should be every time during this course. I understand. Every time it's just yes. I got a question. In your slides yesterday, you always showed the DT and IGT reaction with the sun. Doesn't it carry on the sun? Right. Right, okay. Just- Hi, Howard, nice to see you. Thank you for coming.
Sorry, I can't stay long.
You're, well, a couple of minutes, okay? All right, remember Peter?
Of course.
So this one.
So where are the undergrads?
Yeah,
Where are they?
they never come.
Should be a.
I know, I know.
Okay, Corey, that's useful.
Yeah.
I think the problem.
I did lose you somewhere
No.
in the middle, but
And we're dying,
Took some notes
we're
on us.
dying from it because none of us could stop working.
but
None
yeah,
of
I
us
think it's
could
really
do
wonderful. And
And it's just like.
I met with Thomas yesterday evening. We
Almost
discussed
until
the
that.
muscle yesterday's and we were
Yes.
questions.
Yes.
Most of the
Nobody,
questions are.
nobody has even replaced what people has been at 3% load, which is zero.
And there's the marketing. Took some data last night.
Yeah,
It was,
He was clear.
I'm quite pleased with it.
Scientific, he had effort. And we, it's not that we don't put in effort, but nobody, no, but he is irreplaceable as if he did. So I should have gotten 160 years and executed as far as I'm concerned.
So this is, it's not the first time I took a,
So how much,
I'm serious with the
I do medicine on the third,
So with the removal of the
and
cell.
resolution.
So what, basically what I have here is,
We can get incredible results, I'll be showing
50 minutes.
results today.
and this
Lunar
blue line is one
We'll
wire.
be showing tomorrow at
Which
the
also
Cold
uses
Fusion
them.
IAP.
They have like
Found a way
Well, with
to make it
resolution,
look like a
they're
resistance.
sold as being, accurate.
And we reported over the last couple of years, we
I'm
get
sure
energy
about-
gains out.
0.5.
Over the summer, we get.
Yeah, we're sort of getting such that. Yes.
So we see where we're going to go, and I'm really, yes, but it's.
So I have, I get data increments of 0.06 degrees. But again, accuracy, so this is just a result, the accuracy is probably worse than that. So probably like 0.5. And then the red line is the atmosphere. And what I did is I have this styrofoam box in the lab.
Because that's where the.
So put the sensors in there. And then, so that was right here. So that it took some time, but. Then I did here to also put the put them inside the drawer, inside the styrofoam box. So I opened the box, touched the sensors, put them inside the drawer, just have it right there. And then I think what happened here is that because of the mass of the box, the temperature
I'm probably gonna go to 2:30.
And then it was coming up, probably not gonna stay there.
I mean,
So here it's consuming.
Just on aqueous stuff. I do propulsion.
So here you see the one wire is fluctuating between 23.6 and
Let me get some stuff up. I think I got a slide here about.
so that's just what I know. But the thermistor, I'm very pleased with the thermistor. It's actually very, so here, the noise we're seeing is really on the level of
If you want copies of the papers, let me send email to this.
So this is,
I'll send it to you
so this
anyway.
one,
Just send some email. Otherwise I might forget.
the first 2 digits are pretty stable. I'm actually thinking,
People's contact information.
I don't know, for some reason. the
Yeah.
computer's gonna have it. I don't think this is.
Well, you could send email there too, because I'm gonna make a list up of the people who were here. And that, what we're gonna do actually is we have a group on the internet. Where we meet. So I'm gonna try to nominate everybody in
I wanna
the
seal
group.
the box.
That's a group, and you know how it is with guilds.
Let's seal it on one side and put the center.
All guilds.
And then put the whole thing in ice.
Yep.
So then I can-
Works the same purpose. Okay, so email in and. you'll have-
Yeah, that's all you gotta do, and then I'll send you the URLs to the paper. And,
I'll wish that people that.
we got about 55 papers.
Yeah.
And here's none of the guy in this, right? He was the one with history.
Okay, sorry, I'm taking up your break.
I mean, yesterday I did a presentation.
I just did that last night, I was quite excited.
Yes.
Although I've got like more stuff there. Yeah, it's hosted by. No, we put it in.
Yeah.
Everyone seems to. Managed to focus on which everyone was very disappointed because they thought this didn't work. So much discussion about the Philips neutrons. Very disappointed and well, you have to stop this. This is ridiculous.
I want the rest of the so I see it.
Trying to figure out what is going on. So I want to learn something because
Absolutely, I remember when it was announced today, in '89, we had, this could be something real. I wasn't involved in the field at all, I was involved in internet.
Okay.
And so I've been watching this for years. Now, we're coming to something that years ago.
okay.
So I'm not experienced, you know,
Okay.
I'm at the end of the road, well,
And if you have another table, you know, electron donations, then sure. This may be a good way to.
Yeah. That's on someone.
I don't know. There's a little bit some steps with
Yeah, there's
can actually have some impact.
But at least I can tell my bosses, we're getting close. These are the steps that need to happen.
Okay. So you're actually considering this as a coming feedback.
I am. I'm not saying anyone else in my
But
company.
you have a boss that
I have a boss that's listening, so I need to feed in.
So now I'll
Where they're at, what they discovered, what they need to do so far. And these are things that need to happen still.
Yeah.
But, and then it's a guess on the timing. But at least we know, we can be watching for, okay, this stuff's happening.
Shall we get started?
We should know what's happening.
Hi, Chris. Welcome back. Before I get started, I have this address where if you email me your name, if you haven't done it, there's a copy on this sheet, just pass it around. I'll send you 10 papers a day on Cold Fusion, and that way if there's any questions beyond what we did, you can either read that or then contact me. Okay, let me just say one more thing. I'm Dr. Mitchell Swartz. I'm from Nanotech, not MIT. And I really want to thank Professor Hagelstein because I think without his understanding of the physics, I think a lot of this would not be understood well at all.
That understanding has guided some of your work.
Yes.
Okay. Okay. Yesterday, we did an overview. We talked about the electrochemistry, the materials, and the importance of controls. Thermal controls, calorimetry controls, noise measurement. And in fact, as we pointed out, there's a new control we do where we take the cold fusion active material, quench it. And that way we're even triple assured that what we have set up is accurate. Today, we're going to actually talk about some aqueous cold fusion systems. These are both Fleischmann-Pons-like and things that we did that were slightly different from what Fleischmann-Pons did, making them high impedance in the solution, making flux through the metal so they would be non-equilibrium. And we did this through control of the flux equations, which I think are, from an engineering point of view, one of the most important things for controlling cold fusion. What we did yesterday, we talked about why cold fusion is important, the abundant safety, the pollution-free, the importance of the density being way outside of conventional electrical production and electrical storage devices. And when we plot out here by energy density or power density, we're way out here, and that's really important. The other reason it's important, several of you got a cup of coffee. The caffeine is about 400 micromoles, 500 micromoles. The deuterium in your coffee is around 900 micromoles, and if we were to correctly burn that with cold fusion to make helium-4, we make enough excess energy that if we were taking it out at a 1 watt rate, it would last 18 years. You're a cup of coffee and you'd end up with a product of water, ordinary water. And if we took it at a higher rate of 100 kilowatts, for example, to take a plane off the ground, we could have a 2-hour flight just from the deuterium in your coffee. We talked about what materials are needed. Peter has explained why palladium is important. We talked about the fact that when you have defects in the palladium, major defects, large cracks, it does not work. And then we talked about the application of an electric field intensity. And when you put on an electric field, positive charges, the holes in the metals and the cations in the solution go to the cathode, and the electrons go to the anode. And as we told you, the anode is the site of corrosion. And when you have movement in an applied electric field intensity, either from free charge carriers or dipole orientation, you get both polarization and dissipation, and they're linked together. And the last thing we talked about to get ready for today was how electric conduction really works in water. It is not just the orientation of the dipoles, but there is a movement of deuterons in heavy water or protons in ordinary water towards the cathode, where once they reach the cathode, there's a microwave rotation, an infrared asymmetric vibration, and you have a Volmer reaction. Okay, and here you see that where these are linked together, and we end up getting drift ellipsoids, and at the cathode we get, as Peter spent quite an amount of time talking about, the Volmer reaction. We talked about temperature measurement. Temperature is not heat. Heat's connected through the specific heat of the material and the mass. These are well characterized, and we've been able to measure these quite precisely, even going back to Lavoisier, as I pointed out. We do one other thing where we use the thermal conductivity of the metals when we make our measurement and materials, and we try and set up good geometry. Good geometry is not only important for optics. If you want to do really good calorimetry, you got to think about it too. And when we do the calorimetry, as I'll show you today in aqueous systems, yesterday we talked about, we like to have a multiplicity of ways of measuring that we're really getting excess heat, both in parallel and series. So here in parallel, we'll look at delta T, we'll look at heat flow, and we'd like to divide by the input power because that lets us compare different systems. And then we do time integrated, ohmic controlled calibrated, waveform check calorimetry. I showed you why it's important to check the waveform yesterday, so that if you put a square wave into your calorimeter, if it's an accurate calorimeter, you're going to get a square wave out, and you better check. And I also pointed out that it's important to do noise measurement, because if you drive your system below the noise level, you'll get a false positive. So here is our cartoon of what we do. We take a cold fusion device, we put it next to an ohmic control, we're measuring temperature. We show it just here, but we measure it at a multiplicity of places. In addition, we have, with a separate group of sensors, we measure the heat flow out. And we do other things. For example, we'll take out of the core, we'll take our heat flow through the heat flow sensor, then we'll end up putting it into an engine, like a Stirling engine. We'll end up making electricity through thermoelectrics. So we have a multiplicity of ways in parallel and in series of verifying our measurement. What I'm going to show you today is where we've gotten in cold fusion. We're going to show that we have excess heat. We're going to show it's reproducible with high gain today and tomorrow. And then we'll talk about electricity production. And of course, the ultimate grand slam home run is to then take that fungible quantity of electricity, because we can convert it with any other system. Okay, so let's start. These measurements, I'm going to talk about classic cold fusion, which is palladium heavy water. And I'm also going to introduce nickel ordinary water, which has deuterium in it. And we also did doping experiments where we added increased amounts of E2O. And the reason we call this high impedance cold fusion is because we add no additional salts to the solution. It's often common in cold fusion since 1989 that you add lithium, you add, Randy Mills began adding potassium, other materials. We looked at a variety of these things and nothing worked better than high impedance. And from that we developed metamaterials, and I'll come to that in a bit. So this is what we'll go through today. First thing we want to think about, again, are controls and some definitions. One word that we're going to use over and over is the fusor. This is a wound, cold work, wound spiral cathode that we use. And as I will show you in the second part of this, we have much more energy production for the same input compared to all other systems. So those are the fusor systems. OMA controls, if people don't use controls, I tend not to believe their data. And what I'd like you to do with each of these graphs I show you, I want you to try and figure out off the graph, does it show excess heat or not? And excess energy is the difference between what we get out, the heat, and the dissipation that we put in, minus the initial dissipation. Okay, so here, for example, is just thermometry. This tells us nothing. We did get excess heat with this, though. But just looking at temperature, like is often done on the internet for a number of people, I can't tell if we're getting excess heat from this, even though we melted the container. This was a nickel ordinary water system. We were getting about 25 watts excess with most of these. And we ended up melting the container, and the fusor was okay. But here, for example, let's take this palladium fusor with ordinary water versus platinum as the anode. And what we find is here's our OMA control, here's our fusor, and this is the raw data coming out. So here's our input power in watts, which we read over here in blue. So for this much input power, we can see it stabilized here. We get out this temperature, and yet we put in a smaller amount of input power and we get a higher temperature with the fusor, and we didn't reach equilibrium here. So we'd like to eventually see equilibrium because that really tells us what's going on. If we look at the equilibrium points, here let's take our input power for a similar experiment. This is palladium, heavy water, and platinum. In this case, we have bilateral anodes, but we're looking at a rise in temperature of the control, a maximum of about 21.5 degrees centigrade, versus diffuser, which is 25 to 30 for the same electrical input power. Now remember, when I do input power, unlike a lot of people in this field, I use V times I. I was trained that way as an electrical engineer. My background is electrophysics, both here at MIT, and then I went into medicine and I studied electrophysics and surgery, radiation oncology, and now psychiatry. Anyway, what we see here is a difference in power. This is the incremental excess power gain. Actually, we haven't converted yet. This is just the differential in temperature. We'll come to that in a second. Here we see the delta T for various input powers from 0 to 8 watts to the fusor. We have a number of controls. And we see that for any input power, here about 1 3/4 watts input, 4.5 input, we get a higher temperature at equilibrium for the cold fusion system versus an OMA control, which you really ought to always have. Okay, thermal power spectroscopy. Now let's take our systems and try and convert our thermometry to real calorimetry. So here's our thermometry. Here's a function of time. Here we're driving the cold fusion device. We take a break and then we put the input to the OMA control. And we can see that for the power in, we get this temperature. For the same power in, and actually less, we get a higher temperature again. Here, we get equilibrium. So let's take a look here. In this system, which we ran, we began loading at minus 10 degrees. As Peter points out, you want to get high loading initially. You'll load either cool or very hot because you want to preserve the lattice. So here's our input power to the control. Power is right off the left axis. We're putting in about 1.7 watts input power, and that's what we get out. And in terms of the fusor, which is the cold fusion device, we put in less, we get out more. We put in about the same, we get in much more. So here is our excess power. The power gain is the ratio of this to that. Here is it integrated out, is energy here. And so we have 100,000 joules roughly that we put in. We get out just a little bit more than 210,000 joules. So this difference is our energy gain. Okay, we've got power gain. We read off the left. the difference between these two, energy and here. This is a clear case where we get excess heat. Yeah.
I just want to clarify something. By going from temperature between temperature and power, is the parameter that you measured temperature, and then you calibrated power based on the control power input?
You measure it by the differential. At equilibrium, you want to have 2 points across. We talked about this yesterday. What is classically done is to look at the difference in temperature and heat flow.
Okay.
And I pointed out that there's a term that's often left off, which is the positive term, the T1 plus T2, and that ends up the energy that goes into the mass of the system. Often left off, but you put the two together, you get the square wave out.
So generally, in equilibrium, you get a delta T between the outside and the inside, and you know what your power input is from the VI, and that's how whatever delta T you get as a function of VI, that's how you get the calibrated
Two
power.
terms. There's the flow term, the heat flow term, and there's the rise in temperature. Okay, because that's what it is. You put input in, you're either going to raise the temperature,
Right.
depending on the specific heat and the mass, or it's going to flow up. Yeah.
So that's the case for sort of relatively simple climate counterintuition. We also have heat flow sensors in some of these experiments.
I've never heard of heat flow. You can measure heat flow directly?
We'll show you.
Oh, okay.
Okay, we'll come to that in a bit. It wasn't until, this is 2003, they didn't have them available till a few years later. So I'm going to show you the whole range when we added the one we could. Yeah.
Your power going in is straight DC? There's no...
DC.
Okay, so
All
no
DC.
factors, none of that.
It's not pure DC. I mean, it changes here, but within the rise time differences, it's essentially DC. Good question. And this is heat after death. We'll come to that later. So it doesn't matter which order it is. Here we do the control. Here we do the cold fusion device. Here's another experiment where we do the cold fusion device. We do the control. And we can see a nice match here for the control. You've got to have controls. And here we're getting a power gain of about 30%, 40%, but it's real power. It's excess, and we're making it from the helium, and it is of an energy exceeding the materials that are there. We can run it for a longer time. If we look here in the energy that accrues, we see that when we have a control, we're going to get a parallel line between the input energy and the output energy. But when we have a real cold fusion device that's active and working, we're going to get a slope that's higher. So the things to look at are a difference in our output versus our input and a change in slopes on the energy. Let's look at another set. Here we have a run for about 3 or 4 days. This was taken when Popular Mechanics was interested and featured our stuff. This is back in 2004. So here we have, we're putting the energy either into the control or the cold fusion system. This is a high impedance cold fusion system. It's palladium, ordinary heavy water with no additional ions added. And we, as I pointed out yesterday, we pay extra for this. Normal heavy water runs about $200 to $300 a liter. This is $3,000 a liter. What they do is take out all the paramagnetic ions. And as I pointed out to you yesterday, and as you'll see shortly, TAFL is the killer of cold fusion. We'll come to that in a bit. Okay, so here we see a power gain here, power gain here, power gain here, power gain, power gain. This is clearly excess energy that we can measure quantitatively here. This is the energy that we put in, this is the energy we get out, and the difference is the excess energy. This is our power gain is the ratio of this to that. Our energy gain is that minus this. Questions up to here? Okay, let's look at a few more. This is just a log plot where we do the same. And again, we see that we get a nice match for the ohmic control. And for every input power, we're getting more out than we put in, except initially. It takes a little while to turn on because we have to load it. Back in '95, we presented in fusion technology, which was then the name for the organ of the American Nuclear Society, the fact that we were getting excess energy in nickel. Now, this must have been an interesting paper because when we submitted this to the patent office, probably over 40 times, it's been removed from the wrapper each time. And it was discovered in federal appellate court that they had removed it. And anyway, Here with this measurement, we see as a function of time over 35 hours. Power is here, energy is here. So here's our power curves. This is our input power is in blue. Input power to the cold fusion system is here. Nice match for the ohmic control. And for the cold fusion device, we're getting more up than we put in. And it's about a ratio somewhere between 1.3 and 3.5 is what we were seeing here. Here we see with energy, we see that, again, we measure the noise level. That's always a good thing to do because you want the input to be above the noise level. And we see that it comes back to the noise level, but here's our heat after death. And here we can see that, again, we get a nice parallel match, but there's a superlinear rise if we get the excess heat on energy. Let's look at another one. This is a nickel spiral fusor in ordinary water. Now, when we do the ordinary water here, it's misnamed conductivity water. It's really as resistant water as you can get. It's 18 megohm centimeters when you take out all of the ions, but you can't keep them out of the water because CO2 goes in and it forms carbonates. So even if you have the best, purest water, which is 18 megohm centimeters, in a few hours it'll drop to about 1.2 megohm centimeters as the CO2 enters. So that's essentially what we really have here when we call it pure water. It's not pure, it has some carbonate in it, but it is high impedance. So here we have our ohmic control, two more controls, and again we see more output for power than input. Here we see less output power coming out than input for the ohmic control. We have our noise measurement. We see it comes back to the noise level. And again, with the energy, though it's very tough to see here, under the controls, they're parallel, and we get a superlinear rise if there's excess heat. Now, we do other kinds of controls. We will make pure calorimetry. What we did in the open demonstration that we did in Peter's lab in 2005 is we took one of these cold fusion systems, high impedance cold fusion systems, and here we see two containers, and in here we have an ohmic control. It's a carbon composition resistor, probably taken out of a TV set from ages ago. And here we have a palladium cathode and a platinum anode. This is pre-filled. We would fill this with heavy water when we brought it up to his office. We fill that too, and we put these in electrical series. So if we have a current source here, a Norton equivalent, it doesn't really matter what you do. Since they're in electrical series, the current is the same from one and the other. And what we then did is measure the voltage across each of them. It tells us the input power to each, and we measured the temperature. And although for some reason it's not here, but I will come back to it, and we got excess heat now. So yes, Florian.
So there's no lid on that, right?
Yeah, there is. This is before it's filled. You absolutely want to isolate your D2O from the air. We spend a lot of time doing it. It'll pull the H2O out, and that'll interfere with your loading. So when we keep D2O as a reagent, we'll have 50 layers of parafilm and other materials to keep the air from entering, to get the ordinary water.
Are these containers insulated?
Pardon?
Are these insulated, these containers?
They're thick polypropylene.
Okay, so you were not concerned that the heat would.
Oh, and these?
Yeah.
You want the heat to come through. That's what we're measuring. And notice these are not good geometry. I mean, what we do now is we'll do linear movement of the heat in one direction.
Right.
Here it was 360 degrees, but that was 2003. It was the best we had. And we put a thermometer on it, and I'll show you the results. When we do, here's a dual calorimetry one, a dual calorimetry experiment. That is, this is in a calorimeter, that's in a calorimeter. So here is our ohmic controls. There's a nice match. Here's the power into the ohmic control, power out. Here is the power into the cold fusion device. That's the energy. Here's the power into the cold fusion device. Here's the power out. Notice there's a little lag. You've got to load. Even if you loaded it for a couple of weeks, often it'll deload a little over time. It takes about 15 or 20 minutes to get it back up to the conditions where you get the excess heat. So that occurs here. Also, you have to pay, as Peter showed you. It's easy to get to 0.4 loading. You want to go higher, it's going to cost you. So there's a little endothermic depression here, if you really look at it. In the end, we get out, here's our excess energy. It's the ratio of this minus this is our excess energy. We didn't get any excess energy with the ohmic control because the difference here is 0. And we got a little bit of heat after death. We'll come to that in a minute. And again, you see the non-parallel slopes where we see real cold fusion, and parallel slopes where it's just ordinary dissipation from the Poynting vector. Before we brought it to MIT, we did an experiment with Gene Malev. That's the picture on the internet where he's got a big smile on his face. One reason why you all ought to go into cold fusion, it's very endorphin producing. When you finally get it, you will have your victory points. You'll be very happy. And this was the experiment that we ran for 7 days. We began it on, I think, Tuesday, and he was murdered on Friday, unfortunately. We've never had anybody even come close to replacing him. And we put off popular mechanics for a couple of more weeks. But this was that experiment. And here you see the nice match of the ohmic controls. Here's the input energy to the fusor, the output energy. So our excess energy is here. See, there's a match for power with the ohmic control, and here's our power gain. Okay, optimal operating points. One of the reasons I think we do so well is, one, we use high impedance systems, because I believe that people have been missing cold fusion because of TAFL, and we avoid TAFL, as I'll show you in the equations, by maximizing loading everywhere we can. And what we do is, when we take a cold fusion system, I like to examine it at all kinds of input powers. And so here, for example, here's a fusor system, heavy water, palladium, coiled cathode, platinum is the anode. And we are looking at input powers from 0 to 8 watts. And we're getting out excess power from about 1 watt to 4 watts. And by plotting it as a function of input power, we see that after a certain point, we're not getting out as much as we want. I mean, here's the controls. We get no excess energy from the controls, no excess power. This isn't energy, this is power, but power times time gives us energy. So there's no excess power from any of the controls. And here we find if we increase the input to around 3.5 watts input, we get our peak output of about 4. So we're getting a gain, a power gain of about 2.1, 2.2. And if we go higher, it's going to fall. So I believe that what we're seeing here we're having Volmer inadequacy. Here we're having too much TAFL. And we'll get to that in the equations. This was the demo at MIT. Basically what happened was we had been conducting these experiments for several years, making a lot less publicity than people are doing it on the internet these days. And Gene Malev came by the house. He says, boy, you've got to show this at MIT. Peter came out, he agreed, and we brought it here to ICCF10. And what you see here is, in here are the 2 calorimeters, and we sort of did overkill. We showed you how they were in electrical series. We measured the voltage across each of them with 2 voltmeters, and they showed the same voltage. But we were able to absolutely show the power dissipation to each of the cells, and we got a higher temperature out off the cold fusion cell than the ohmic control. And when we looked at the power gain, what I was trying to do was show these optimal operating points. So on Tuesday, the biggest day we had the demonstration here, several hundred people, what we showed was that as we increase the voltage, the power gain falls reversibly. I mean, because you can then lower the power and bring it back. But I wanted to show how to control these systems, and that if you increase the power beyond the peak, you end up losing the power gain, and that's what we showed. So here is no gain. We still got a little gain here, 130 to 150%, but nowhere as before. And here, as a result of the 5-day run, this was our optimal operating point manifold. So we see that for this device, you want to drive it around somewhere between 0.5 and 1 watt input power. And beyond that, we get diminished gain. Okay, as a result of that, we took the cell, we ran it off and on over
about a year. And the following year, this is Brian Josephson, Nobel Prize winner, came by and he says, I hear you got a cold fusion cell working. I'd like to see it. I said, sure, come on by. And he came by, and this was the run we took with him. And here we see the ohmic control. If this is done perfectly, the ohmic control should be right between these two lines, but you can't always do it. So in the best ones, I'll show you where we do it, but it's very tough to do because that means you have to know a priori what the impedance of your solution is going to be. But here, when Brian Josephson was there, here's our energies, input and output from the ohmic control. Here's the energy into the cold fusion cell, the output energy. We got his endorphins going. He's been on the internet pushing cold fusion since then. We got an excess heat with him of, I think it was 140%. We measured 190% for power gain, but when you measure the energy gain, it always is a little bit less. So we got 140%. He was excited. I was depressed because we previously gotten 250%. Now it's 140. And that's what we see inexorably with these cold fusion devices till we add magnetic fields, which we'll point out on Friday, which is we see an evanescent fall in excess output energy until we learned how to do something else, and we'll come to that. Here was the power gain as a function of input power in the Josephson experiment. You see, it's about 1.4 to 1.6 power gain. And yet when we went up to more, we get less. Okay, an important issue. There is an optimal operating point. Questions? Okay. We looked at a lot of materials. We looked at, here's palladium heavy water with a number of materials with diffusors. These were very high. We learned how to get here are the controls. We never got any excess power with them. These are with the nickel materials. We'll talk about them later. The take-home point of this is that with these aqueous systems, whether they be nickel with ordinary water, or nickel with ordinary water and deuterium doping, or palladium with deuterium, we get excess energies beyond what is possible by energy storage, or even beyond the energy in the materials. It can only have a nuclear origin. Now,
Question, please. Have you ever put a oscilloscope on your input voltages to see if you're getting anything unusual happening in your cell?
yeah, we did.
It's all studied.
It's not perfectly DC.
Yeah, but there's no unusual.
No, we're not putting spikes on or anything. What you see is when you get cathode reaction, we get low dielectric constants in front of the cathode. And the low dielectric constants will decrease the current, increase the voltage, depending if you're using a current source or voltage source, it won't. So it does, you do see some changes. I'll show you this is one.
A quick question.
Yeah.
What I'd really like to see, and I don't know if it exists or not, is a really good analysis of, you said that the output, the excess power can only be of nuclear origin, because it's more than this source, more than that
Right.
source. Are there any really good descriptive analyses of the possible sources of hidden, non-nuclear energy?
Yeah.
Somewhere? That's something I'd really like to see for a skeptic.
There's no sources available. I mean, it's been analyzed and there's been found to be an absence of those sources.
And I'm looking for a good written out, well communicated, detailed version, explanation of what those sources were looked at. Not just for your experiments, but for some of them in general.
I think
I would like to see
it's fairly common to do that.
Well, I'm thinking that there does exist documentation on specific sources. So for example, there are papers that go on for recombination, which was proposed as a possible source of error. There's other papers which talk about the loading enthalpy, which is at this point pretty well characterized. In the basic flesh-and-ponds experiment, there's not really a whole lot else. I mean, the skeptics have argued that there's internal stresses and strains that can be released that can reduce some energy. And there are papers where people have analyzed that. The headache is that depending on which experiment you compare it against, you're down by 3 or 4 orders of magnitude.
Right.
And at some point, the folks in the field start to lose a little bit of interest in pursuing it.
Oh. So there isn't anything that's really good at explaining all of that,
Oh, no, there's plenty of things that are good, but they're good at explaining one of them at a time.
Yeah.
I don't know of anybody that's gone through it, said, look, let's consider them all systematically, let's provide all the references to yours.
That's what I was getting at. If there is anything, something I'd love to see.
I don't know.
All right. Thanks.
Okay, so let's move on. We're going to talk about flux. Just as Peter has analyzed the chemical potential as his way of looking at the elephant of cold fusion. Cold fusion, in medicine, we used to say that if you want to know medicine, study tuberculosis. You'll understand everything. Because in studying the pathology and the treatment, you really cover all the medicine. And the same thing is true of cold fusion, not about medicine, but about science. And it is astounding. I mean, almost everybody in the field is looking at this phenomena in different ways. So Peter spends a lot of time looking at chemical potential, and I'm slowly coming up to speed. I spend all my time looking from the engineering of Navier-Stokes, and that's what we're going to talk about. And the reason I find it important is I believe that's why we're successful, is understanding how deuteron flow and palladium flow can give us excess energy and how. Now, the obvious way is that we know that the excess heat that comes out of the palladium suddenly comes up once we get the loading above 85 to 90%. But how does that interact? Another way we know is when we look at the excess output of these devices as a function of current density that's applied, there's often a threshold current density. These are clues that flux have a role. So how? We're going to look at, these are the kinds of flux we're going to look at. And the reason I find it a very successful theory is, one, it explains loading, it led to CODEP, it led to what we call a catastrophic theory of the active medium, but we'll come to that. It led to optimal operating points, metamaterials, which is the next section. And what I think lets us do these other things, controlling heat after death and photoirradiation of the cathode. All right, so let's talk about flow. Here we have an anode in this Gundankin experiment. We're not going to show the power supply here, but here's a power supply connected to the anode and connected to the cathode. And what happens is the electric field points from the anode to the cathode. The anode is the site of corrosion, and all of the cations are going to drift towards the cathode. So we have one vector, we have a flow vector in the solution, yet interesting things can happen at the cathode. We could have it enter, that's Vollmer. We can have it go up in a gas, that's Tafel. We can have it go into fusion, that's Fleischmann and Pons and Hawkins. So there's 3 ways it can go, and to me, it's a zero-sum game. There's also this, we call this interstitial flow in the palladium, and we'll come to that in a bit. But it's a zero-sum game. It comes in, and the fact is, if it's going up, it's not going in, and it's not going to the other thing. So it's MIT, it's time to write out the equations. We can say that the flow of deuterons has 2 terms. It has a flow from the concentration gradient, which is what's here. We use the B for diffusivity because we can't use the D because we're already using it for deuterons. And the second term is the electrophoretic term. So here is the electric field, minus the VDZ. And the amount of movement current, therefore, depends on the concentration, which is a function of position and time, and the electrophoretic mobility. These are the two terms that control the flow of the deuterons. Okay, now I'll show you a movie afterwards where what we see in these high impedance solutions is before we get the excess energy, we get the bubbling on one side. And I remember when I presented at ICCF 10, I had a disagreement from the crown head of the meeting that this didn't happen. There's always bubbling on both sides, but you can't argue with what you see. And I will show you time-lapse pictures of bubbling on one side. You do get bubbling on both sides in a low impedance system, but in a high impedance system, this is what we see. And we see that when we get excess heat. And we get a different kind of bubbling from large cracks before it's quenched. And I'll show you that too. So let's review here. The flow has two terms, one from diffusivity, one from electrophoretic mobility. And we do the following. We take the equation and we divide by concentration. This gives us a first order rate constant. So here is what I think is the most important equation of cold fusion. And this equation tells us that the first order rate that enters the lattice is equal to what comes in from the applied electric field, almost a duh, isn't it? Minus what goes up in the gas. Kf is the amount that you lose to fusion, but even if you're getting a joule out, a watt per second for every joule, we're only burning up 10 to the 11th, at the most 10 to the 12th deuterons, so that number is pretty close to zero. So it turns out that the first law of cold fusion is if you want the material to enter, you want this term to be high, you want that term to be low. And to me, this is important because most people say that cold fusion is fusion by electrolysis. It's not what the equation says. The equation says it's 1 minus electrolysis. In fact, as I've been pointing out to people since March 24th, 1989, if you see the bubbling, you lose. And to the degree you see more bubbling, you lose more. And that's a problem because most people like the bubbling. It gives them the endorphins, they think something's happening, but they're not going to get the excess heat. Now it gets even more interesting. Let's take this equation and put in the Einstein relation, which is QV over KT. Well, it's mu over D is KT over Q. So we end up getting that the entry rate of deuterons is equal to the ratio of two energies, the ordering energy from QV and the disordering energy from KT. There's a geometric factor here from the diffusivity over the length. But again, minus what goes up in a gas. Cold fusion is not fusion by electrolysis. It's fusion in a lattice that you can screw up if you get electrolysis. Anyway, that is the most important issue here. JG is not desirable, and I'll show you a picture. It's not working. Try again. I thought I had my Murphy already today. I guess not. It won't do it.
We try and play the video.
Pardon?
We try to play the bubble in the video. The video they have
While we're waiting.
the diffusor, the electrolysis.
It's not gonna let me fix this.
drawing?
I'm gonna just skip to the next section, there's nothing I can do.
Try skipping over that one slide, just to
It won't go.
the other side of it.
I will later. I'm just gonna skip ahead, otherwise it could be a disaster. Metamaterials. When I first came to MIT, we studied materials alone, and it was really a right field because there's so many. The Laboratory of Insulation Research, where I was working at the Veliparium Titanate, and there was an incredible array of materials being examined. No one knew about metamaterials then. The fact is shape can change the function of a material. And it's usually in optics that this occurs, but we think it's occurred here as well. What happened was when we began looking at the power gain of materials, here are some that got no excess energy, no power gain. Most of the nickels didn't, some of the nickels did. And all of a sudden, we had one configuration, because I tried everything. I tried mats, I tried woven. We did this fusor, and it stuck out amongst all the others. And we never found anything that worked as well. And finally, Gail Verna said, well, why is this one working better? And we decided to look at the electric fields within. And this is what we found. Let's take our fusor. Here's our equation again, the flow, the diffusivity term, the electrophoretic term. And here's a background on metamaterials. What's different about our system is that our solutions are very high impedance, minimum of 200 kiloohms for a solution. Really good ones, 800 kiloohms is what we'll have for the solution resistance, compared to the milliohms, 50 to 100 milliohms for the palladium. And so when we analyzed, in our numerical analysis, a number of things, we discovered something amazing. And that was the following. The Fleischmann-Pons system, you could model, or most people who do it, have an anode and a cathode that's separate. Here we're looking down from the top, and we see it comes to equilibrium. All of the fields come together, and that didn't occur in this. In our system, what occurs is the electric field goes through the metal. It's as if we're creating, because it's not infinite conductivity of the metal, there is some electric field there. So what we're creating, we think, is additional flow within the metal, and that was the IP term. Remember, there were 4 terms from the diffusion of the deuteron coming in. It can enter the metal, it can go up like Tafel, it can end up going to fusion on the order of 0, even if it's successful, because of E equals mc squared, and it can go through the metal. And what we did is we looked through this in a number of configurations, and we found this to be a major effect. We don't hit an equilibrium system in this. And we end up getting fields through the metal that we don't the other way. I really got to go back. Here, for example, let's look at this cathode. Here we're getting excess heat, and here we're actually able to salt in the system and get rid of the excess heat. And what we end up producing is bubbling everywhere else. We get gouts of bubbling with the loss of heat. I think the important point here is, 1, we may have a metamaterial. We may have a situation where the shape of a material changes its function. 2, of these, the fusor that you can read about in the papers I sent you and will send you if you send me the email, was the best of our performing devices. And therefore, we've got to consider, are there other metamaterial shapes that we can use in everything we do here to improve function? Okay. I'm going to try one more time to go back. That is important. Green.
look forward to hearing from you.
Thank you. Let's take a break for a second. I'm gonna bring the computer down. And hope it does. 5-minute break if you want.
Take a quick 5-minute break for those of you who just tuned in.
Couple words. Maybe we should record the computer.
So it was freezing up on it, we tried to go beyond that one.
Yeah, and then it wouldn't load at all, so hopefully something gets fixed.
Can I get one of your cards? Okay. Where's one? I'll just make sure.
Give the computer all 3 finger salute, control all deletes.
I got a print out. Hang out.
It's 3 or 8 now.
Yeah.
It's a base.
Plus, we got 10 viewers online right now watching. It's 11 now. Keeps going up and down. Like this.
Yeah.
Coming in and out.
Yeah.
It's doing a live stream right to YouTube now. So it goes to our YouTube channel here.
Basically
It's a live event.
Yeah.
Yeah, on there.
In what?
In my
Should be up right on the now YouTube channel.
You might be able to do that. I just kind of like to say.
Okay.
Sorry.
I guess so. You know, I wouldn't mind. I wouldn't mind plugging into maybe get a bit more bandwidth. You know, I plug straight in. I'm not sure if I get better upload quality, video and audio quality can upload better quality if I plug straight into the internet. Yeah, I'm wondering if that would imply video as well, or if it's just. I hope so. I would hope so. I'd have to get a LAN cable and find a connection.
I can't get down to keep it crashing. What do you want me to do?
It's just my Wi-Fi without my team guests.
How do I start it?
Oh, no, I work for Cold Fusion now. For them. Ruby's a friend of mine.
Not the next one, the one after.
These past 2 years. And this year film for me.
Does the slide,
My
the next slide is the one that's probably causing the problem. Next slide, skip over it, go through it.
I tell you what, I'm gonna do is not erase this.
There are certain groups that seem to be ready at that level for it. And I just, it seems to me, I think a lot more engineering work needs to be done.
All right, we're ready to start again.
Yes.
All right, we're going back to flux. I had to erase a couple of slides, I'm sorry, in order to move ahead. I'll tell you what the slide showed. We had one of our systems with very high excess energy with no bubbling, and that was what I wanted to show you. Apparently the computer crashed. So we jumped ahead to co-deposition. What I'm trying to show in these surveys is that there's a lot of ways in which this Navier-Stokes equation can help us in cold fusion. And if you're not math phobic, you ought to consider it. So for example, let's take this equation. Here's our flow equation. And we've made a flow equation for deuterons, and we made a flow equation for palladium. And in the solution, we can do both. And that's called co-deposition, because what we're doing is we're taking the cation deuterons, making a cathode fall in front of the cathode, and the same thing happens with the palladium. And here's conventional cold fusion as a function of time. You see the loading is very slow, and that takes 2 weeks to a month. And if you do cold fusion in this theoretical plot, what you see is with co-dep, there's two curves where you get the loading at a high value very quickly. Now, Spey-Wars, Stan Spock and Pam Boss, Larry Forsley, Frank Gordon, actually use a slightly different method than we do at JET, where when we deposit, we co-deposit onto palladium. They co-deposit onto copper, nickel, silver, and other metals. And that has a couple of effects. One is when we deposit on palladium, I don't see any junk on the bottom of the container. We get it all captured on the cathode when we co-deposit slowly. The other thing we find is that there's a lag in the loading. It takes us a little bit longer, probably because the volumetric palladium may sop up some of those deuterons. But I'll show you the results. A lot of papers have come up out of cold fusion. And here is the result. Here's some raw data from cold fusion, where here's our aroma control. Here's the palladium fusor. And these are various temperatures. Let's look at the temperature in the center. The aroma control is right next to the fusor, and the anode is off on the side. So here's our power in. We can see that for about the same power in, we're getting a high temperature out. And that's what we see with co-dep, is that we see here's our thermal power spectroscopy. We're seeing power on this side, energy on that side as a function of time. Here, the electric energy is going into the fusor, the cold fusion system. Here it's going into the aroma control. So we get a match here. We see parallel energy rise like we do always. Here we see a superlinear energy rise because we're getting the excess heat out. And almost for every input of power in to the cold fusion system, we get more power out. here's a cold fusion system. We use dual anodes. Dual anode fusor is what we'll do is we will deposit palladium onto the cathode and then switch to gold. So it's listed here as a platinum gold because that's what we're running, and we're having palladium and PDO-D2 in the. Can I get rid of that? Hold on a second. Sorry. Okay. Since about 2006, we've been putting cams in some of our devices. So here you see an optical cam looking at the fusor. Here we see an infrared cam. And when we get the excess energy, and only when we get the excess energy, we see a near infrared output that we'll talk about. We see some other interesting electro effects when we do code depth, but I think that's beyond the scope of this introductory talk. Optimal operating manifolds is another spin-off that came from Cold Fusion. Came from the quasi one-dimensional model of loading. OOPs, that's what I showed you before. When we look at the response of the Cold Fusion system to input power, whether it's tritium production, helium-4 production, heat production, whether it's in nickel, whether it's in palladium, we always see an up and down, a biphasic response, except in one case where we see two, and we'll come to that Friday. But that was only a recent discovery. Here's one of them, as I showed you before. Input power is here. Our excess power gain is here in watts, so it's not really gain. Gain is a number that we multiply the input by. This is our actual excess power out. So for every watt here, each second we're converting 10 to the 11th to 10 to the 12th deuterons. And there's a peak. So we have a manifold, we have a peak where we like to drive it, and we think that we lose because we're getting too much taffel here, and we're getting not enough loading here. Now here, for example, I went and once I discovered these optimal operating points, we called up everybody we could to get the data. So I called up Mel Miles, who had published his helium-4 data, and it showed commensurate amounts of helium-4 production with the excess energy that he saw. And he published the current, but not the voltage, which you need to derive the power. So I called him up, I said, could you give me your input powers or voltage so I can calculate it, and he did. And then I called up Stan Spock to get the tritium results from Spaywars. Also, they had only published the current, and they were compliant too. And my gosh, when I took the power rather than the current, we got these nice curves where the heat overlapped the helium production. Cold fusion is said to be a non-reproducible science. It looks as if it's reproducible, but where we drive it is not reproducible. These things are linked. Anyway, here's heat production in nickel. This was the errata work with palladium black. This is tritium production without CODEP and with CODEP. And so what we see are operating manifolds as a result of those engineering equations. And we use these in order to get the systems to work. Now here, for example, after we talk about the aqueous systems, we're going to talk about propulsion systems, Stirling engines. And even with the Stirling engines, here we have paired Stirling engines. They're in electrical series, so the current is the same. We measure the voltage across each like we did at the MIT demo. And here, this even at lower power, the one with the cold fusion device is hotter, and you have to start both Stirling engines. But this one, the one with the ohmic control will stop spinning, and the other one kept spinning 11 miles versus 0. Okay, so what we see is here, when we look at the power gain in our Stirling engine, so we're measuring the power deep in the calorimeter, we see that our peak power is at 6 watts input, and we get a gain of about 2. Our peak power that we saw out was 25 watts for the Stirling engines. And it turns out that if you want to drive them where it's a little more complicated because there's 2 operating points for the engine, but again, that's advanced beyond this. We talked about that already. Here, let's look at some optimal operating points. This was the one we did with Brian Josephson. Here we see when you first make a fusor, this is what we get. We get almost nothing. We get start down here, it comes up a little more, evolves, and it changes over time. And we see that, in fact, here's Ed Storms' data, who argued with me that there are not optimal operating points. So I had him send me my data. I had him send me his data, and here's optimal operating points in his data too, which you can either use or not use. Now let's look at this input power to codec. Here, people say you don't get much power up from cold fusion. One sec. And here we're getting excess power up from codec of 2.5 to 3 watts. We get a lot of excess power up from aqueous cold fusion, despite what's said. But the reason I'm showing you this is these grow with time. They change with loading, okay? And in fact, as we grow the code depth, here we can see the power gain rise. And I did a rough calculation. This is not measured, it's estimated, of the thickness of the co-depositional layer, though this is the other one was a measurement. Here we see the impact of adding heavy water doping to ordinary water with nickel. We get optimal operating points there, except for the fact, as I'll show you on Friday, we can destroy the nickel, unlike palladium, which is resistant to deuterium. Nickel falls apart under some conditions, and after a certain amount of time, its electrical resistivity changes. Here it goes from 8.8 micron centimeter to 8.0. We never get excess heat again. So metallurgical differences are important. These are optimal operating points. They have grossly similar qualitative shapes. The peak is where you should drive the system, whether you want to make helium-4 or heat. That the peak is only one possible operating point, and it may be the reason why cold fusion was said to be irreproducible. Okay, they're incredibly useful. You can, okay, bottom take-home point, by analyzing the data this way, we see that a vast set of experimental data lines up in a very orderly form that is otherwise not explainable. We see that in fact we can get peaks along the electrical input power axis, and that totally dispels the irreproducibility myth. People claim it's irreproducible because we're driving at different amounts. I mean, if you want to look for one thing and you're driving in the wrong place, you're not going to see it. On the other hand, if you do it correctly, we've measured a few gains, and if you treat it like an antenna, you can calculate it out like an engineer. We're not going to really talk about here, except I'll just summarize it. Palladium does not like to hold deuterium at high temperature. Unlike some metals where the deuterium, where the solubility increases, it spits it out. And I believe what happens is when you look, this is the amount of loading. As you raise the temperature, it deloads, and I believe that's what drives it into the vacancies. I think that you have, I don't think we have uniform temperature. I think we have regions where there are differences. And as a result of the inhomogeneity, I think that's what drives us to the vacancies. We built some devices with it. We talked about the metamaterials. This is a little out of order. So lucky you've seen it. Controlled heat after death. Fleischmann and Pons had a cell that they ran, and eventually remember, they weren't trying to prevent TAFL. Most people in cold fusion don't care. But if you do, your solution is going to run dry, and their thing ran dry, but it kept giving out excess heat. So they gave it the terrible moniker, heat after death. In fact, what it is a series of excess power, tardive thermal power. Tardive means it comes after you apply the electric field intensity. And the heat after death is the time integral of the tardive thermal power. So for example, here in our dual calorimetry system, we are driving our fusor here, this is the output, and we shut it off here, and we're still getting heat out that we don't get out of the control. Identical calorimeters, identical masses. We're not getting the heat out. This is tardive thermal power, and if you integrate it, that's heat after death. Here's another one. Let's look at this run. Here, this was a really good run. Luce Mullen, who was head of RLE here, came to visit, gave some great ideas. He was head of electrical engineering when I was here. And he pointed out to me, what you really want to try to do is get the control smack bang in the middle. And it's tough to do because you've got to know what your solution and metal impedances are going to be before you start the experiment. But when you do it right, here's a great run. So here's our input to the fusor. Here's our output to the fusor. And our input and output energies to the ohmic controller so close they just align. Here's our power input and output. Input to the fusor, output to the power. Here's our noise measurement. Here's our heat after death. And eventually it comes back to the noise level. What we tried to do then was, hey, let's take the heat after death and do work on it. So I think this was the first run in history where somebody took heat after death and electrically moved it to an ohmic resistor in a second container to heat it up. And that's what we did here. We connected it up here, and the heat after death fell, and here we're measuring temperature in the second solution, the noise level rises. So we're actually taking the heat after death and doing work with it. Questions? Okay, here's another one where we're seeing this tardif thermal power called heat after death. And the reason this is important is I found that when we looked at it, we got various time regions, different segments that were linear. Maybe we are looking at the regions within the palladium where we're getting excess energy. Maybe there's a region on the surface from CODEP. Maybe there's a region up to 40 microns deep, which we call within the lattice itself. And I think that's what we're seeing here. So we see an early, intermediate, and late excess energy. And I did some modeling. We used to have Corsair 601. I don't know if they have it anymore. But you can do a lumped parameter analysis of your system. And so we did that here. This is our fusion impedance of 6.6 picomoles per volt second. Our leakage resistance is incredibly higher. See, this is how it comes out. We're getting a leakage impedance of that many nanomoles per volt second versus our we have charged up. By analyzing like this, I think we learn more about what's inside. Okay, another thing that came out of the use of the quasi one-dimensional model of loading these Navier-Stokes equation is to look at the impact of light on the cathode. So here, for example, here we have a container. Here's our ohmic resistor. What could look more resistor than a carbon composition resistor? We have our cathode here. Here's the anode over here. Here's one of our temperature measurement devices. And we shine light on it. So this is about somewhere between 5 and 10 milliwatts of red light. And what we find is we get an increase of about 300 milliwatts. And unlike some people, I do a control with the laser. We do a control, and we do, here's the laser with light. Now what's interesting is we think, in addition to what Peter and Dennis Cravens and Dennis Litz discovered about terahertz irradiation and the impact on what Peter will talk about tomorrow of the phonon pool, we also think there's an effect on the loading. I think that because of skin depth, not all of the light's going to get in the metal. Some of the stuff's going to be reflected. And what we found by measuring it was that the loading increases. And there are changes in the solution, and I sent you the paper. Again, if you didn't get it, send me email to what's on the board. I'll send you the 10 papers from last night, and we'll do another 10 tonight. These are all from the advanced course. We'll skip that. I think there's one more section here. Questions?
So your cathode with light. Have you tried other ways of stimulating it?
Yes.
And how did it work?
Okay, let's talk about that. The best way to stimulate is with temperature. Okay, one of the early things that Fleischmann and Pons discovered is that, and all of us experimenters who've done cold fusion have discovered, is that slight increases in temperature improve it. And there's, people will talk more about that tomorrow. Another thing, some people have found other types of irradiation help. We've not found that. And that'll be in some reports I'll send out tonight. Near infrared emission. Stan Spock had published this back in, I don't know, 2003. They showed the cathode has flickering heat spots on it. Now, to me, in the absence of a control, you can't prove that's excess energy, excess heat. So, one, he looked in the far infrared. He had some medical devices and they were using them. So we decided to reinvestigate this and do a control, put an OMA control in and do some other controls so that we could not only look at it, but see which of these spots, if any, were there when there was excess energy. We decided to look for it. And we found a couple of things. One, we found out that we needed two controls. This is our fusor here. Here is a gold anode, and what we did was we did a number of serial photographs. We ended up analyzing the location and the intensity coming off as a function of excess heat, and this sort of summarizes it. What you're looking at the insets here is the near infrared intensity integrated over during the fusor over its site and during the OMA control over its site, okay? And these two regions were examined during putting power into the control, power into the cold fusion device, and we found the following. Here we see the input to the fusor. Here we see the input to the OMA control, and we see the temperatures. And what we can see is that the near infrared only came out when we had the excess heat coming out. It wasn't a function of temperature. Here, for example, the OMA control was at a higher temperature, and it didn't produce that. It was flat. So I call this non-thermal near infrared output. And we saw this in this particular experiment, we're getting 80 times output. Here's our delta T divided by P. And when you take delta T, we're going to spend a lot of time on this tomorrow, and divide by input power, you can take the ratio, and that gives you the power gain. Here it's about 80 in that experiment. And here we're also measuring heat flow, and we're getting more heat flow out. So we're confirming that we have excess energy by two different systems, and during that time, we're seeing near infrared coming out in a greater amount than from an object. We saw this also with the nickel ordinary water system. Here's the near infrared when it's at the XT. This was the first one we did. And what we now know is that we get non-thermal near infrared output only when they're at the peak. Then we began, what we reported recently was looking for gamma emissions. And what I did was in our back of the envelope rough and ready experiment. This year we're going to do it with a good germanium detector. But to do the rough and ready experiment, we took a Geiger counter. Here we have a nano. We haven't really talked about the solid state devices. We're going to do that tomorrow. These are aqueous devices. But in the solid state devices, they look like a resistor. There's two terminals. We put on a voltage anywhere between 100 and 2,000 volts DC. And we get out excess energy, as we'll show you tomorrow. So what I wanted to do, here's our active site right here. And I took off all of the thermal materials, the insulations, to show it to you. And we put the Geiger counter right on the center. So the first thing you got to do is we sampled for 2 weeks because we want to make sure there's not extraneous or cosmic or galactic reasons periodically coming in, which can do it. We want a long baseline. And over that time, we found that these were our counts. And so the average is around 12. And if we look and we put on a high pass filter, we look at how many times we get out a count of beyond 15 per minute. There's this infrequent. And if we look above 16, it's almost zero. So we set it at usually 16.5 to 17. We want to set it at a level. We're not doing a gamma spectrum here. We're not really doing a complete measurement. We're looking for the incremental increase from a cold fusion device. And it was really lucky we did this autonomously, because when we measured it, it turns out I put out more gamma radiation from my potassium-40 than these cells do. A nanor, when it's fully active, puts out as much penetrating ionizing radiation as a banana peel. So fortunately, we set this up to run autonomously for a month at a time and did not have people coming by. So we didn't have the potassium-40. That's most of the background that you pick up per year. And here's a typical run we did. This is usually these counts are about 6 seconds a count. So this is something like 24,000 seconds, a third of the day. Here we put input to the control, input to the control, input to the nanor. And during this time, we get more of these bursts than we do here. We got none in the control. We get none when we do the OMA control. And we get a few bursts here. And so we integrated those up, what we were actually measuring. Now here, by the way, here's our excess energy ratio. What we're plotting here is the rise in temperature divided by the input power. So as I'll show you over and over tomorrow, you can easily calculate power gain by taking the ratio of dt over pi to here. So our power gain is this ratio. And here we did it with a background of, one of these is with a background of thorium. The other one has no background. But again, what we see, sometimes when we turn on the electricity right away, we pick up. But most of it was during the nano. We can skip this to later. The basic point is that when the cold fusion system is on, we get about 2.5 nanosieverts per hour. And that compares to each of us, which puts out about 46 nanosieverts per hour. So you're getting a bigger dose sitting next to those 3 people than you would next to a cold fusion device that was putting out a watt. Now that's not a megawatt. We might need shielding there, but for low-level devices, we don't see it, but we see something. Okay, so the important thing is there is an output, very small, nowhere near the amount that we expect from the amount of excess heat we get. That's 1. 2, the amount we get out is insignificant compared to the biological background that we pass through every day. Questions? Okay, what we did next is try to image it. We took CI39, which was developed initially by Dr. Lee for hot fusion, then used by the Spa-Wars group with co-deposition, and they are the leaders in looking for CR39 from whatever penetrating radiation is coming into it from the co-dep system. So we followed on to their lead, and Pam Boss sent me these 3 CI39s. Here you see a calorimeter. Everything's been taken out of it, all of the thermal isolation, the fire bricks. I wanted you to see the location of the nanor and the OMA control next to it. We put 1 CI39 on top of it, 1 here half shielded with aluminum, and the other one went into my lab notebook. Okay? Now, the trouble with CI39 is you want systems when you read them. What happens is when you have penetrating ionizing radiation go through a material, 90% of the effect is indirect effect through water. 10% is direct effects on the material. There's no water in the CR39. So what you're inducing are free radicals in this material. And then by applying sodium hydroxide for several hours, pits occur. So pits are the legacy of penetrating ionizing radiation passing through. And the number of the pits tells you how much went through. And the point here is just that you've got to skip the superficial crap. Okay, so what we measured when we looked at a histogram of these defects, above the NANR we saw this many. Next to the NANR we saw this many. Shielded by the aluminum in the same chamber was this many. And my lab notebook was here. So we can plot them out like this. We can look at all pits. We can look at the small and the mid-sized pits. It turns out the ones that are really helpful are the large pits. And when we plot it out, like here are the actual CI39. And what I do is I have an imaging device we developed that lets us see specifically the pits in the center and gets rid. See the schmutz on the surface? We have a system to get rid of most of the surface crud. So we can really do a good quantitative calculation. So here's where the NANR was. And when we image it, that is, we just take the counts. What I did is I divided it into squares. I gave it to 4 people to give me counts. What you do is you have them go around twice, because the first time they go around, they're not quite sure what they're doing. They get really good as they go around to the end. You have them go around again. And so you can get the counts, and we put that into it so we get an image out. And it turns out, here's our NANR. Here's where the CI39 is. And we actually have an image of the heavy pits. We see that over the NANR, we see large pits, and we can image the NANR. So we can see that we are producing some, nowhere near the right amount, but some penetrating radiation on the order of biological background, but not zero, from these devices. Future issues with this are, I think this was the first time anybody's imaged these devices. The reason I did it is I developed positron emission tomography over at Mass General to help image cancer. And we did the first images of cancer. We published it in the British Journal of Radiography. And so I was very interested in imaging these as well. And the next question is, why is there not ionizing penetrating radiation in cold fusion? I mean, one, it's been forbidden. It shouldn't be there anyway. Two, what did the equation show? What really surprised me, I went back and looked at it, and people had not looked at the equations, which have temperature in it. The classical Bremsstrahlung output power calculation is in the Navy Blue Book. And it's in all of the, but these equations go back to the 20s and 30s. They were used theoretically and experimentally and shown to be valid. And when you plug temperature in and skin depth, you find out the following things. One, the forward radiation as a function of temperature when you go to hot fusion to cold fusion drops by 10 to the 18th to 10 to the 21st. So first of all, you wouldn't expect, based on our knowledge, to have gamma emissions. I mean, that's Heisenger's third thing, is cold fusion can't be real because everybody walked out and lived, right? Well, it turns out if you look at the equations, one, it doesn't give you a forward emission, but drops by up to 10 to the 21st. Two, the frequency changes. It goes from penetrating ionizing radiation frequencies to the near infrared at cold fusion frequencies. And there it is skin depth locked. And if you don't know what skin depth is, send me an email, I'll tell you about it. It's basically this, it's how far radiation goes in. But it also tells you how far it can go out. So that's a second reason why I think we don't see it. Okay, questions? Nothing?
Rachel, what's the argument for not having optimal points? Or operating points and not having optimal operating points among your peers?
You only see the optimal operating points when you plot as a function of input power. Most people don't. If you look back at Mel Miles and Fleischman, they were plotting current. They didn't even report the voltage. They reported the current. I just was lucky I was trained here as an electrophysicist. So I looked at power, and to my astonishment, everything came out with, not like Gaussians, but of that kind of shape. And it didn't matter what we looked for. And if you look at their data and you don't plot as a function of input power, it's up, down, then it looks not reproducible. But plotted as input power, it looks very reproducible. It is. Dual adjacent calorimetry. I showed you that one of the things we do is we take two calorimeters, one with an ohmic control, one with the cold fusion device, which also has an ohmic control in it. So we're having two ohmic controls. But this way we can normalize for the calorimeter. What we tried to do, and it was a failed project, but I'll just show you anyway. We did dual adjacent calorimeters, we put it together. So that has a problem in that now when you heat up one, it impacts the other. But also, if you're getting excess heat, you can pick it up from the other one. So there's some advantages and some disadvantages. We set up a model house to do this. And basically, we used, for these experiments, a very large anode, an anode plate instead of just a wire. This was the picture I was going to show you. This is cracking off a large amount of excess heat and no bubbling. I mean, I was amazed. We were driving this at, does it say what the voltage is here? These are up to hundreds of volts and no bubbling. And we were driving it continuously. This is not fusion by electrolysis. It's quenched by electrolysis. Anyway, here's our output from the dual adjacent calorimetry test in the model home. There's a mouthful. This is looking for the fuser and the fuser volume, the fuser output, and the control volume. The bottom line is that we got an excess power of 150%. And when looked in the contralateral volume, it was 138%. It's a way of double checking that you're getting it, but there's a lot of crosstalk, so we don't like that anymore. One thing interesting here is VOC. I didn't mention this. In ICCF 10, we reported the importance of open circuit voltage for following these devices. Now, it's often mislabeled in the literature in cold fusion. It's called the reference voltage. It's not. It's an open circuit. We are measuring here open circuit voltage. And what we find is if the VOC, that was the question I asked Peter today, how does the chemical potential relate to these VOCs? And the answer is there's a second piece. We've got to add about 0.9 to the chemical potential. But when we see a VOC above 0.7, we have had excess energy. If we see a VOC of 2.4, we had a lot of excess heat. So 1.8 is pretty good too. And that's just another check, okay? Here is a second run where we had 490% power gain. Questions? I will do one more. And we'll do electricity tomorrow. The last two sections on aqueous cold fusion is the running of propulsion devices and the generation of electricity. So let's talk about motor devices, which we've done for, I think, more than a decade. It's Stirling and his Stirling engine. And I used paired Stirling engines. What we do is within here is a cold fusion cell. And the opposite one is a ohmic control. We'll have the electric current go through both in electric series, again, measure the voltage. And in addition to doing calorimetry in the core, we're doing sort of calorimetry here too. We're looking at temperature of the base, temperature of the surface. We're getting as much data out of this as we can. And I'll show you why in a couple of seconds. When we look at the excess power, we're getting a power gain on average for all these initial experiments of about 170%. and to 220%. And we got optimal operating points, as you saw. And here's where it gets interesting. I told you that we measure both in parallel and series to verify. And here's a case where we're doing, I'll show you first 4 ways of verification and 6 ways. Here what we do is this fusor was run, heavy water, platinum anode, dual engines, and what we're getting here is an energy gain by calorimetry of 150%. Power gains are higher, like I told you before, but we're measuring multiple ways. We're measuring by heat flow, because now we've picked up the heat flow device. So we measure DT over power input, heat flow over power input, calorimetry. We measure ratios of electricity production and ratios of propulsion. Here, for example, is our delta T over input of the fusor versus the OHMA control. Okay, so the ratio of these two is our power gain. And we can see over time this increases. And there's a second one where we're looking at calorimetry. Nice match here for the OHMA control, just like it should always be in the center if you can pull it off. Here is our energy gain. Here is our power gain. Here's our heat after death. And this one, what we also did was look for electricity. Let's see if that's here. Here's our heat flow over power input. So in addition, here we're looking at delta T. Here we're looking at the heat flow over power input. So these ratios are what the power gain is. Remember, there's 2 of them. That's why we're not seeing them sequentially. Okay? We have 2 devices that are in electrical series. That's why we're seeing one over the other. And here for the same, it's not the same power input, but the same electric current. And when we divide by power input, we're getting a power gain of 2. Here is the calorimetry, again, a nice match in the center for this one. Here we're looking at delta T of the Stirling engine. So we're not only looking at our calorimetry at the core, we're looking at calorimetry at the machine itself. And we see a couple of things. One, we see that when the engine turns on, we lose some of the excess heat. We're going to see that's really important here. Here's 6 ways of confirmation of excess heat. So we have our calorimetry. We have our input power normalized delta T. We have our heat flow normalized to delta T. We also did the electricity, the propulsion. And this is really interesting. When the Stirling engine turned on, we lost the excess heat in the core. We're not getting, it's as if we're taking the energy out. Okay? So we're not going to get excess energy at both places. In a way, it's nice that it went back down. As soon as the engine turns on, we lose it at the core because we're taking it out. We'll skip this. This really belongs with the advanced course. We're trying to make UAVs with it.
What's the difference between
when
you take the engine out with the Stirling engine and you're just exposing that side of where the heat's coming from to the atmosphere? Does the Stirling engine take out more heat than
I think it does.
expose it to?
I think it does. Well, also it depends if it's conduit limited. I mean, if these are situated above, where the as you see from the output, the Stirling engine is on that plate. So I think that wouldn't be true if you had a tube and you were limiting the heat flow. But right now, all of our heat taking out is limited by the Stirling engine itself.
And you keep mentioning delta T that you're measuring. What are the actual temperatures? So is this working at 200 degrees C? 100?
Good question. Generally speaking, with heavy water, I would limit the temperature rise to 90, 95 degrees centigrade. At $3,000 a liter, you don't want to boil off too much too quick. So these are actually fairly sealed vessels. They're not totally sealed because we don't want to kill anybody. But they're essentially sealed and will rip open at high enough pressure before we get catastrophe. Any other questions? Yeah,
Did you mention UAVs?
I did, but we're not going to talk about that here. I'll go to the next one.
Okay.
That's the advanced course. This is the introduction. I'll do one more on electricity. Give us more time to do nanomaterials tomorrow. We want electricity because that's really how you can have this system of cold fusion in people's homes, doing things more than heating things up. And we want to do it because it's ultra clean. We have trouble doing it because Carnot whacks us. And when we try to make electricity, our efficiency is only about 17%. And so we need a power gain, an energy gain of about 8 to 15 to pull it off. And I'm going to show you now the failures we've had, because I think the next time around we're going to succeed. But so far we haven't done that well. In the early 90s, we were just trying to make electricity. And that's not too hard. You just take a thermoelectric, you heat it up, and you can see that one LED is hotter, brighter than the other LED. But the real trick is, how do we go around in a circle? We can take our thermoelectric converter or put it in a fuel cell or a custom conversion. How do we take our device and put it into feedback? And that is what is most interesting, which I'll go to now. When we began with energy conversion, we thought we only needed an energy gain of 5. It turns out it's probably closer to 10 to 15. And that's why we think we'll pull it off with the nano, and we couldn't quite do it with the Fusor. Here what we're doing is, I'm going to show you, we take the Fusor, we put it through a thermoelectric converter. The fuel cell is actually down here. Boy, is this wrong. What we do is we take the thermoelectric converter, we put it through a first stage converter to raise the voltage. When you do a thermoelectric conversion, it's a fraction of a volt. And remember, we're driving the Fusors at hundreds to 1,000 volts. So we need 1 or 2 stages to bring it out. And we have an interesting movie where the take-home point of this is we set this up to use a fuel cell. And fuel cells are driven by the Laplace equation, making these bubbles, which is actually tied into the Patriots game and the football. But skip that. What happens is when you make the bubbles in the fuel cell, it's a very inefficient process. And what we found when we began doing this is I did it totally wrong in our time to do this. Here's what we found. We found that when we made hydrogen to store in the fuel cell, we wasted 13% of the energy going through the feedback loop. When we converted it back to electricity, I always thought, I mean, these are not supercapacitors. These are a way of losing energy. When we finally took the hydrogen and oxygen and put it back for feedback, we lost another 54% of the energy. It's awful. I mean, everybody says fuel cells are the way to go, and it's not. We're losing 60% of our power here. To my astonishment, we lost 5% of the power in the switches and the wires. I'm glad we did this. You know, I think we're farther ahead than hot fusion. Hot fusion dreams of getting this far. Here we're measuring what our losses are, and next time, we, in the end, only had 6% energy available to put into the final stage to go back to the Fusor. So we failed in this one too, but we're getting closer. We're learning, we'll never do this again. We fixed this, and we're getting better. We're getting better. I think we'll be able to pull it off.
So 16x would have given you, 16, 17x would have given you.
Would have done.
What you needed. What if you took the fuel cell out of the loop? What would the number have actually been? You just didn't.
We might have been close. This time we're just going to leave it off. We use a supercapacitor, something that'll store the energy without the loss. or do it directly. I don't think we can do it directly because there are reasons why you want to store it and hold it. And this time also, when we do it, we're going to actually try and make it totally autonomous, where we have our driver being stored with a secondary capacitor. We want to really do the complete feedback loop, because that is the grand slam home run of Cold Fusion, having electricity come out for good.
You need a battery or a capacitor of some kind in case the reaction doesn't stay stable. Right?
I think the reaction is stable, but you want to store the energy. I mean, typically your computer driver is going to need 1/4 watt to 1/2 watt power. Our systems are going to take a lot. We've got to get the voltages up. That's where we're losing our efficiency now, is basically to go from 1/2 volt to a couple of volts, we only lose 4%. But now you want to go from 4 to 500 to drive it. That was what the fuse are. See, that's why I think we're going to win. We're getting high energy gains with the Nano, and we don't need the voltage that we did, so we don't have to do the drive up. Anyway, this is our goal, and we're going to try and finish it this year. We've also tried, I'll just do this in passing, we've tried to make direct electric conversion. It turns out you can do it with nanomaterials, but the efficiency is incredibly poor. The efficiency was 10 to the minus 14, barely measurable with a Keithley electrometer, but not zero. And what was interesting was when we put on a magnetic field, we actually got rid of it. We'll talk about this on Friday, which is the impact of magnetic fields. And some are good, some are bad. It depends on the direction and the relation to the applied electric field intensity. Questions? Yeah.
What type of thermoelectric converter would you use?
All kinds. The easiest one you can get if you're doing an experiment is the Melcor type. I mean, there are so many available. The problem is the efficiency is so poor. Now, that's one of the reasons why, again, Peter's a leader, is going to change things. There are people here working on temperature conversion devices. When you deal with the efficiency of a thermoelectric, it's really two terms are multiplied together, the Carnot efficiency and the efficiency of the device. And if you take out Carnot efficiency, it's hard to get above 40, but Peter thinks that they have a device now that is above 40 before adding in the Carnot term, and that will also help. But we need a higher temperature for that. So we're moving along a lot of tracks, raising temperature, decreasing losses, increasing energy gain, and eventually we'll move towards home plate. Yeah.
If you look up, if you construct a system, hypothetically speaking, to achieve like an over unity type setup in which, are you running into energy conservation issues?
No, because what we're taking is deuterium and making helium-4. And the mass is slightly less for helium-4 than D plus D, and C squared is a big number. So that's where the heat comes from. There is total energy conservation here. And there's momentum conservation too. That's why the helium, I'm leaking out Peter's talk for tomorrow, but that's why the helium ends up sitting in sites and shutting off the reactions. And probably why the nanomaterials are so effective, because there, the distance for the helium getting out is shorter.
A quick follow-up to that, then how does Stan, I don't want to say his name, Stan's Spock, thank you. Stan Spock has found tritium. Now, isn't that a byproduct of the deuterium fusion reaction that, by the logic that's already been presented, isn't that a branch of the fusion pathway that's totally suppressed by the proposed Cold Fusion model?
Actually, that's a good question. First of all, we don't see tritium the way we get excess heat. These are two different regions, okay? And I'm not going to discuss that too much here, but what was your other question?
So tritium and excess heat are not associated with one?
No, they're separate optimal operating manifolds.
All right. Because it strikes me as interesting that tritium is being produced.
Oh, that's the other thing. there are probably a heterogeneous set of sites that give rise to these reactions. For example, we talked about the fact that there's cold fusion in the volume. Okay, and Peter will discuss how the volume helps the physics. We talked about how there's cold fusion on the growing surfaces from co-deposition. There may also be something like hot fusion on the asperities. When you apply thousands of volts and you have a sharp edge, you have a contracture of the cations, all of the integral of the voltage goes across a small area. And we may be producing hot fusion-like reactions, okay? Plus, if you're not using pure D2O, there's some H in it as well. So there's a lot of whether all of the reactions are in fact hot fusion, hot cold fusion.
So you're suggesting that it's created in a second corollary reaction, that's not the primary reaction, or the one creating the most.
Or the same site. I'm not convinced it's necessarily the same. I think there were where cold fusion occurred. I think there are 3 or 4. I think you've got the deep volume, you've got the superficial volume up to 40 microns. You've got the co-depositional surface that grows if you grow it and use it. And you have these asperities. And I think those are the least like cold fusion. And you don't always get the asperities, but you often do. Any other questions? Then we'll see you tomorrow. And tomorrow we'll talk about nanomaterials, how we got cold fusion. One more thing. If you want to get a copy of the papers, send email to iap@nanortech.com. I'll send you the URLs to the 10 papers from yesterday to tonight, and at about midnight tonight we'll put another 10 up.
I think we ran a little over, except for yesterday. It's all.
Thanks for watching, guys. Glad to be here. I'm watching live too. I'm right here in the classroom, so I can see all you guys' comments on YouTube. For those of you who are talking to me on YouTube, I can see on there. So don't forget, tomorrow, if you have a question, you can ask it live right there in the comments feed right on YouTube, and I can see them and ask your questions in class. So thanks for watching. Take care. Live from MIT.
Okay.